It's a nice. Where's the presenter? I guess it should start in a couple of minutes, actually. Yeah. Is it going to be online? No. So there's one offline talk, and the rest of them will be online. And I understood this last minute because changed.
This one is going to be online or offline?
It's offline. And the rest will be an online stuff, so we'll just have a large Zoom call, I would say. Yeah, maybe a question. When there will be online talks, will we see the presentation here? I guess it's manageable. Yeah.
One talk?
You have the only offline.
Не, ну, да. Как keynote speaker начала выступление. So she started her talk in the beginning, the mentioning of the GD. But was touching on. This was a touching moment.
Yeah, I mean, yeah,
Is she come from the university or from George Washington University? Or she's just visiting?
No, she's an endowed chair, professor, and she's here a few years.
How many students do you have?
In computer science department, we got 600 or 700.
Wow.
So we have 4 masters, 4 bachelor
Overall, for all the courses, like whole science. So we have one like humanity faculty that is just teaching English, and that's not many students there.
No, but we have like business school here as well, which is really big. What do you think we start?
no, I think we should I think we should start more or less now. Is it going online already? Yeah. So thanks everyone for coming. So I would like to start our section on data analysis and machine learning with a big thanks to our host in Armenia. Now Armenia going through hard and dark times, and I would like to especially thank the host for having the strength and courage to help us still organizing this event at these hard times. So my name is Evgeny Tsimbalov, and I have a PhD in computer science, and right now I'm a machine learning scientist in UpTech, and together with Dr. Maxim Panov from TII, Technology Institute, in UAI, we will be chairing this session on data analysis and machine learning. This year we had around 17 submissions, and only 5 made it to the final publications paper. A little bit of more, but we would like to, and unfortunately most of our speakers couldn't come for different reasons, so I would like to thank the speaker who came for coming, and now we will be having a first offline talk. Oh, I can read it from there. So is it about detecting design patterns in Android applications with Codebert embeddings and CK metrics, and authors are Ginjve Dlamini, Ahmad Usman, Leonel Karkwang, and Vladimir Ivanov. Please thank our offline presenter.
Thank you. Do I have point?
Interrupt? Yeah, so you have 18 minutes to speak.
Uh-huh.
I will tell you well 2 minutes, and we'll have 5 minutes for questions.
For questions. Can I use a clicker? Is it here?
Yeah, it should be working. Please check.
Good. So limited time, but nevertheless, the topic is fascinating for me. And but first of all, a couple of words about why I'm working in this direction. I'm head of the lab of the NLP lab for software engineering in Innopolis University, and we have a big contract supported by Russian government in like 7 years to develop tools for software engineering automation, for generative models and generative AI applied in software engineering domain specifically. And especially my lab is focused on code and text representation for understanding of code, source code, and for summarization and similar tasks, and analysis of the textual information. And this talk is about motivated by specific problems that software engineers, but not only software engineers, but some managers of software projects may have in real life. So many applications are being developed. They just stored somewhere, but sometimes managers of the program managers or project managers, they have this trouble with managing, with understanding what is the if the requirements, if the structure of the project specifically, we will talk about Android applications here, follow some predefined agreements about the architecture, about the design, about the patterns that developers agreed to use when they implement the system. And the motivation of this talk is that, we can try to solve this task, at least partially, using the machine learning tools. And there are typical design patterns, architectural design patterns on the right of this, on the right part of this slide. Raise your hand if you don't know what is MVC, MVP, MVVM. Well, basically they are different approaches to splitting the internal part of the application in Android, like splitting the visualization part from the data management part, from the modeling part, and making these 3 parts decoupled in order to do the development, software development more easy, robust, and so on, and maintainable. So classical metrics for source code, they used like back maybe 20 years, more than 20 years, 30 years before, to analyze what is going on in the software. And basically they extract some information. We'll talk about the object-oriented programming here. and it's well-known approach called CK metrics, when they can be calculated almost from any piece of object-oriented code. They deal with the structure, the methods, and the classes, how they're organized, how many methods in the class, and so on and so forth. And these metrics are widely employed also in pattern detection, not just for some quality of the code, but also to detect patterns. There are approaches, I will not spend too much time for this, but there are approaches that are devoted to analysis of the bytecode. If we discuss Android applications, there are approaches of analysis of the semantic features related to the source code, like training a word-to-vec model to extract some semantic features from the source, and then put them into the embedding of the, in the form of the embedding, and then make a decision about that, train a classifier based on this word-to-vec representation. And yeah, and there is a third approach, like using the CK metrics only. Now you know what is a CK metric. So you run through the project, calculate all the CK metrics for the classes, and then make a decision about the pattern. Our research questions was related to these two things. Like the first one, is it actually important to add something on top of the CK metrics? If it is possible to use a pre-trained machine learning model that will extract features that know something about source code, many projects, and extract features on top of the CK metrics that will be useful. And if it is possible to improve, then how well such model should work. And I'll talk about these two contributions, basically the approach. But that is very simple. Maybe you will have some questions in the end, but it's not that hard to understand what's going on. And the analysis of the embeddings, classical features, if they're useful for the pattern. So the methodology is a bit complicated on this picture. If you take a look. This picture may be a bit complicated, but nothing fancy is happening. You have a project of your application that is Android application, many Java files. You can calculate CK metrics, and then you can calculate the embeddings that representations, the vectors that correspond to each file. So for each Java file, this pre-trained model outputs a fixed size vector. And then the second step is to combine, aggregate those vectors into one single vector, basically. And then again, train a classifier on top of this. So we have this first path using only the CK metrics, and the second path from these source files, application of the CodeBERT model that is extracting the features, like the big deep learning model that extracts features. And then we can concatenate two types of features and then decide either using both of them or only CK metrics. For the classification part, we use the CutBoost, that is a state-of-the-art model. The thing is that here we cannot train basically this part, but usual approach is fine-tune the CodeBERT or some kind of transformer that extracts features here. But here we don't have enough data for training, and that's what the idea why we just use the pre-trained frozen layers of CodeBERT. Okay, just to show the whole process step by step. So these metrics representing the one source file ends up in one long list of numbers, each number corresponding to a specific metric, and then you have this array of metrics, like around 10 or maybe 20. That's actually, yeah, actually more, because we use a extended package. It's 82 metrics. And our hypothesis is that these metrics actually they kind of uniquely identify some object-oriented part, and they measure complexity of the design part, of the design of the project, of the design of this class or whatever the source code is. And they can capture some course level metrics related to course level patterns that are related to the target task. For the code BERT embeddings, I haven't said too much about this, but the code BERT, maybe you heard about BERT, the pre-trained model from Google that is kind of, yeah. And the code BERT is actually similar idea, but the same, almost the same architecture, but pre-trained on the huge corpus of source code. Instead of the Wikipedia and some internet corpus, they use the huge, like basically all GitHub, something like this, and they pre-train and predict the train the masked language model on this data, and then you have this model that is, of course, it's not the state of the art right now, but it's still a kind of application of natural language methods in software engineering world to extract some information from the source code. Okay, and it seems that this it's again just a hypothesis, but this may capture on the patterns on the fine level, more fine level than CK metrics, because this captures the token representation. And but the problem here is that for each file you have a list of kind of documents. For each file you have set of representations, and the question is, how do you combine them? The idea is we tested several ideas, like of pooling, of aggregation, like measuring the maximum, measuring the average. It ended up that we use for the max pooling, we used the maximum, or not maximum, but summation of all these values, and that was we get better results with this approach. About the experimentation, so this methodology again just gets the data, and the question about where we get the data. The data is coming from the repository of like the already annotated data set with pattern labels. So we have, it's very small data anyway, 26 like and 22 numbers, 22 projects that are doesn't have any design pattern. But still, it's if you don't consider training, if you consider only the testing part, it's doable to apply this methodology if, in the testing mode. Okay. So that's the data set. I discussed a bit the cut boost already. Just hyperparameters, you can find them in paper, of course. And yeah, we calculated the classification measures, classification metrics to evaluate the quality, of course. And five-fold cross-validation was used because we have diverse in the classes, somewhat imbalance, but not really huge imbalance, but still we can sample from the data and calculate the error. The results here, the first table shows not very fascinating results, but still it's for some patterns it achieves better results than the original paper on the coach, and that's actually compares the CK metrics only and model that combines metrics. So you can see that for some patterns there is a like drop of the quality, so some the same, but so in most cases it's this is the improvement, and this is also a slight improvement. It can be considered as improvement. Again, it's I'm a bit pessimistic about these numbers because it's still far from good quality anyway. So that's and here we compare this regarding the pattern type. Here we compare how the CK metrics compared to Codebert metrics, Codebert embeddings plus CK. So in most cases, you can see that the improvement over the plain CK metrics without any embeddings is like outperformed by embeddings here. But sometimes you have this example here that is CK metrics is better in this case. Okay, and so discussion about our initial research questions. So we also analyzed the importances of different metrics, and this is a kind of when it comes to the practical application. So you can train a model, you can train a CAD-boost model that will predict the classes or the design patterns. But when it comes to real world, to practice, it's more important to get some interpretation, why the model predicts this or that. So here, the interpretation about this part of the work was about finding the top 5 metrics that contribute to decision. And there actually, there is analysis that like confirms that some of the metrics, some of those 82 metrics are actually not relevant for, not responsible for the design pattern. But these metrics that you should, or you as a manager should pay attention to, whatever you use machine learning or don't use machine learning, you can compute these metrics from the source code from the project and say, okay, this is like indicator of this or that design pattern or the absence of some design pattern. I will not go deep because it's kind of related to domain knowledge here, and you should be a kind of developer in Android or a developer in to understand what does it mean, and maybe it's not that interesting. The improvement that ML gives us on top of the CK metric, as I said, it's not that big, and we call it moderate. You can say it's maybe not even an improvement, but it opens a big question about the applicability of machine learning, of that kind of models in machine learning in source code analysis. It shows clearly that it's not easy task. The current models that, like large language models applied to code, also struggle with analysis of bigger contexts, big, large context, large projects, and so on. They usually process like function level or class level context size. And it's still open question. It's still ongoing research. And I will conclude with these limitations. So the major limitations, of course, limitation is the size of the data, of course, and the interpretability of the embeddings themselves, which is just a list of numbers. And if you talk about the interpretation of this list of numbers, it's not that useful because when you use CK metrics, at least they mean something. But when you consider the BERT embeddings, they may be less meaningful. So we are going to continue this work and develop more robust and interpretable approach, and do the ablation study without the dimensionality reduction. That was maybe for the sake of the performance, we reduce the dimensionality of embeddings, but maybe we can try to do this on a more regular or more granular basis to understand the exact impact of Codebert. Do I have time? 1 minute? Okay, so it's just conclusion. You can find code and source code and data here. This work was supported by Russian Science Foundation and was done at Antopolis University, and I ready to answer any questions on this.
Thanks for your really interesting talk. So it's going to be more and more code, and we need to process it on a more automated way to make it work. So the preference now is for offline participants to ask questions. Do you have any question? Anyone on the room? Okay. Yeah, please use the microphone so our online speakers will also hear us.
It's for online speakers. I want to just to ask, is CodeBird available only in one size?
You mean the input, the size of the...
I mean the size of the model. Yeah. The model, right? The number of parameters.
We were constrained by this not number of parameters, but the input size of the bird. So it's fixed input length. 512 tokens.
I just understood that.
Sorry. So the question is about number of parameters. I think the CodeBird is, we use only one set of parameters, like one pre-trained model. It's not like the bird itself, like it comes into several sizes, small, large, and so on. But the problem here is maybe not the number of parameters, because it's not a big number anyway, comparing to large language models, the modern. But the problem here is the input length. So there is constraint with 512 tokens, and if you want to process the whole project, you should squeeze all these source files into 512 tokens. Some of them just too big, so we cut all the comments, cut some unnecessary. So there was a preprocessing stage to fit, and even if you cut some of the files, they are still not fit into the input of the CodeBird. So that's another limitation, another problem of this approach. So one idea could be to move to the bigger models that actually have a larger input window, size of the input context. That could help, and or just switch to some, in principle, different models that can process the whole repository, not just file by file. Did I answer your question? Yeah, questions? I think, yeah. A question?
Thank you for your presentation. So it's not a question, but more of well, like I want to discuss a little bit. So I think it would be cool if your work, if you'll extend your work in finding the anti-patterns in code, and well, I think that might be helpful. Well, when if there is well, such a system created to, well, as a software developer, I say that when a new code is published and changed, then some changes in the pattern appear, and so not like and to not to measure the whole pattern on the project, but maybe like in a small part of the code compared to the whole project, I think. Yeah, yes.
Sorry.
Yeah, it's a good suggestion. Thank you. And yeah, there are such works like for classifying the anti-patterns, finding the anti-patterns in the source code, and like you, as I understand, your suggestion was classifying of the commits that can break some pattern, and that's it. Yeah, there are such works, and definitely it's beginning. And back to the first slide about the Innopolis group. Yeah, actually we have not only my lab in Innopolis who working in this, but other people are trying to approach different problems. In like these times, it's a bit hard to like even to find IDE, good IDE that will be available. And but so there is a number of problems, of course, for practice and for research. But yeah, thank you for the suggestion. It was not a question.
Are there any questions from the Zoom meetings? Are there? Okay, we don't really have any time for that. So let's thank the speaker again for the talk. Yes, and the following talks will be unfortunately held online, and our next talk is a data-driven approach for identifying functional state of hemodialysis fistulas, entropy complexity, and formal concept analysis by Ekaterina Zvorikina, Yuri Beshchasnov, Mayit Sovgadi, and Vasily Gromov. So they will be talking via Zoom. So please, dear online speakers, share your screen or report to me if you have any problems with that. You have 18 minutes for the talk and 7 minutes for the question. Thanks.
Yeah, I think you have to enable the screen sharing. Then I can share.
Yeah. Could my colleagues please help me with that? So is it really problematic? You don't have the host rights? Yeah. Sorry. Okay. Sorry, we have some technical problems. We'll be back in a couple of minutes.
Host
CCAUA.
Okay. Okay.
So we have some technical issues now. You have some time to grab a tea and prepare for talk and listening. Thanks for your understanding.
Sorry for the delay. We need to open through here.
Yes. Or the next will be online. Ekaterina, can you please try to share your screen now?
It still doesn't work.
Okay, 1 second. Stepanjan, can you please try to give the screen sharing option so Yekaterina could open the presentation? Thank you.
Try now, please.
Yes, now it works. Great.
Thank you. I'll tell you 2 minutes before your time left. Okay.
Yeah, so you can see the slides, you can hear me well.
Yes.
Okay. So, yeah, I would like to start my work with a big sorry that I'm not present offline, but let's try to maintain a good quality online. So our work is devoted to time series analysis in a very interesting case of arteriovenous fistula Brut diagnostics. So I will give you...
Make it full screen,
Okay.
so we'll heal better.
Yeah. Is this better?
Not exactly. Maybe you'll try a different button. So now we have some complicated.
Okay. Not now. Maybe like this.
No. It's the whole slide. The presenter mode should be.
Interesting.
Can you just try Control L?
Yeah, I'll try again from another screen. Wait a moment.
Yeah, it's now great. Thank you.
Yeah, so I would like to give some context about what's the problem with the arteriovenous fistula first. So, as you know, chronic venous diseases are the most common pathologies that we have now in humans. And there is a big occurrence of AI methods used for diagnosing these problems. In our work, we decided to tackle this a big issue only for one group of people with chronic kidney failure disease, especially in dialysis patients. The prevalence of this chronic renal failure in these patients is growing now, especially after COVID pandemic, because people who are going to dialysis, they're facing many issues, and if they cannot go to the hospital in timely manner and have to stay in ambulatory conditions, it of course results in many other issues. So what is this arteriovenous fistula? It is a special insert into the vessel, into the blood vessels in their hand of dialysis patients, which helps them to maintain the always available vessel to provide dialysis procedures. So it's a small tube that comes into artery and vein and stays there for some time while the patient has dialysis, so it can be for years. It's a very well researched method. It has very good results in dialysis. But the main problem with this issue is that the patients can get thrombosis through this small channel because, of course, it's not a natural vessel. That's why, yeah, it's easy to get some toxic waste from other cells and also, yeah, to get basic thrombosis, especially in older and elderly patients. And the issue for the patient is that when he stays at home, the development of this condition can be very fast, for example, in a few hours or one day, and he cannot diagnose it by himself, and it can lead to lethal conditions. But the good thing is that this fistula makes a very characteristic sound that is called the Brut. And usually doctors, when the patient visits them for dialysis, they also check how is the sound of this small channel. And yeah, the sound is a result of the blood going through it. That's why it resembles a bit the heartbeat, but of course a bit different, like a pulse. And usually the experienced doctor can easily diagnose if something is wrong and if the patient needs the replacement of this channel. But of course, in many situations, we are not living in an ideal world. That's why the patient cannot go to doctor every day. And as I said, this condition can develop very fast in any time. That's why we decided to use some mathematical approaches to tackle this issue. And in this study, we analyzed 290 patients from different sites in Russia and used the help of the doctors to analyze them. So our motivation was to propose two mathematical methods of analyzing this fistula brood sounds as a time series and try to distinguish them on the basis of the fact that we think that normal functioning fistula makes the sound of laminar blood flow that is normal. And if it's a pathology, it's close to turbulent flow. And we can easily distinguish these two things. During this project, we decided to first, of course, investigate existing approaches, then calculate our methods, which will be an overlay of entropy and complexity metrics of each sample on entropy complexity plane, and then apply two different clustering methods to classify the results of these two metrics. And of course, interpret our results and compare to the real situation that was given us by the medical professionals. So how do we see how they look like these fistula brood noises? If it's a normal fistula, we can see that it's more or less non-chaotic time series. And if it's a pathological one, it looks very different. In our case, unfortunately, we had, for us, unfortunately, but for patients, of course, it was very well, that most of the patients had normal fistula sounds. Only 50 patients out of 700 records had dysfunctional fistula. And also we had 61 cases when the doctors were not sure if it's pathology or not. Of course, for the doctor, it's easy. He can see the patient next day and decide if something is wrong or not. So for us, it wasn't so easy, but this is the problem of the method. Analyzing these noises, we also decided to go with a short element of sound because we don't see a big difference in the results of our methods if we take a very long time series, long record or not. For entropy complexity analysis, we use Shannon entropy and Jensen-Shannon divergence for complexity. Then we used a very famous Wishart clustering algorithm to cluster the results. So for each time series, we assigned two metrics, entropy and complexity, and then basically clusterize them on the plane. Another approach included attribute object graph construction based on the same two metrics and time series. For each time series, we tried to make it as a binary matrix based on the record, based on the analysis. And then this binary matrix was reorganized to attribute object graph, where each element was an object, and for each object we checked if this binary matrix values were aligned. And this is a simpler example of such a graph. Here we have 1, 2, 3, I think 6 objects. I will show later how it looks for the time series that we actually used, and it will be much bigger, but less easy to follow how it works. So the most interesting part, the results. For the first method for entropy complexity analysis, this is how our clustering results look like. And we can easily see that there are 3 groups of clusters. Here, if the complexity and entropy are low, of course, we think that this is a very organized, non-chaotic time series, and we think that fistula works well. Then the yellow cluster means high complexity and high entropy. So this is a very chaotic time series, and we think that fistula is malfunctioning. And we have a relatively big cluster in the middle, which we consider is, we cannot give a certain answer if it's working or non-working fistula. And this cluster is the question for the next part of our work, how we can analyze this data. Also, we got a very small cluster in the top where complexity and entropy is very, very low, very, very high. And I think this is due to the bad recording of the fistula sound, because it's recorded by a dictaphone or a microphone, and usually doctors speak during this procedure. That's why sometimes we cannot eliminate this sound. For the object attribute approach, these are the clusters that we got. And as you can see, if it's an organized time series, we have very nice scheme. And if it's non-organized, it's looked more like a mess, because most of the objects, most of the clusters, they had a lot aligned, and this is considered as the right one is considered as a bad one. Also, we tried to show how it can look in XY plane, so it's easy to follow. And in this case, this method actually gave a better, more distinguishable results. We can see that there are two clusters, which is good. One means healthy fistulas, and another one means that the patient should go to the doctor. And these two methods, they aligned, but the question is how we can interpret the third cluster that is not very chaotic and not very organized, and why we don't see it here. When we tried to combine this, the results of two methods by simple linear regression, we got, I think, 5 clusters, but still the tendency looks the same. We can distinguish chaotic and organized time series quite well, but we have a very big cluster, a few ones actually in the middle that can be, that we cannot assign if they're healthy or not. Which also, after the talk with the doctors, aligns with the reality, because they also cannot sometimes analyze and assign and diagnose these patients. When we compared our results with the doctor's analysis, we got pretty much alignment, even though we had less than 300 samples to discuss with them. So as a conclusion, I can say that we developed these two new methods of not only time series analysis, but also diagnostics for fistula root sound. Both of these approaches were good and aligned with doctors individually and in combination. We have observed a significant correlation between the classification results, and also we compared it with not only doctor's analysis, but also with some Doppler ultrasound for some patients, and it worked well. Regarding the limitations of the study, of course, it's a relatively small sample size of patients, less than 300. Also, the data was anonymized. That's why we couldn't compare, for example, female and male patients. We couldn't know if they are overweight or not, which can also result in some different sounds. Also, there were, we don't know if they're, the age of the patient, that can also be a big difference. And it's still a black box for us. We cannot, consider if our clusters are the same functional categories that doctors are assigning to the patients. For the future development of this project, our perspectives are, of course, have a bigger sample group, also know more about the patients, maybe the age or the weight, or some other comorbidities that they're having, for example, some comorbid illness. Also, for during the fistula construction, fistula procedure, the fistula first months it has undergone through a few stages of growth, and we can also assume that the third cluster that we see in the middle can be due to the fistula is still how the doctors call it young, and that's why we cannot compare it with other fistulas, and that's why our method can also help to see if the post-operative fistula will be healthy and will work for a long time, or the patient has to have another operation soon. That's it. Thank you for listening me, and if you have any questions, I'm here to answer them.
Thank you, Ekaterina. Special thanks from me as a chair. So you made it in less than 14 minutes, so we could try to keep on track. Are there any questions from the offline? Yes. Okay, I'll start with you, with Dmitry. Okay.
Thank you very much for your work. I'm especially happy that you used formal concept analysis, since this is one of our favorite topics in our department, for example. And the question is about clustering. Whenever you use formal concepts and concept lattices, they're like big search spaces rather than single clustering. What kind of selection tools to find a good clustering, a good partition you use here? Can you comment on it?
Yeah, let me come back to the clusters. Yeah, actually, we didn't develop any new one. We used already described in other articles. Yeah, the only thing that, yeah, I think we only use the extra tool to go through the alignments of different objects through the lattices a second time, just to see if they are combined to more objects or not.
So it looks more like heuristic way to extract a good clustering.
Yeah, even
okay.
I must say that even brute force was faster to go through the lattices than any other methods. Yeah, we used it only because it was faster for us in this case.
Let me allow one more comment. In the beginning of Millennium, I was also a part of an international dialysis center working as a system administrator. And I remember those people who took these procedures 3 times per week. It's very important to support their lives. And one more comment from Jaume Bacherier, the program committee member. He had some relatives who also passed away, and he supports your work very much. Thank you.
Yes, thanks. It's great to hear. It's not useless.
Thank you, Dmitry.
Thank you for a very nice talk. I have actually a couple questions. The first maybe to figure out this clustering was done because you don't have the ground truth labels of the samples, or am I missing something? Because on the screenshot on the slide you have labels like 0 and 1. Why you? The question is, why don't you try it as a supervised problem?
Because here we wanted to try, even for this analysis, what would better to use is not clusterization and classification, as most of the people who work in healthcare AI think. But here we decided to try the clustering because we were not sure how many clusters we will get in the first place. Here, yes, we can see the 2 clusters, but we also would be happy to see more than 2. And if I analyze more data, and for example, if I take another batch with the patients from, for example, different hospital site, it can be more than 2 clusters. And here we're very cautious about given labels. because we are not also sure if it's either these clusters are for health and non-health patient or just chaotic, non-chaotic time series.
Okay, thank you. And the second question, as I understand, you analyze time series, and the time series comes from the sound. Am I correct?
Yes.
Or is it a sound wave, like amplitude, or was it?
Yeah, it's like an amplitude. So usually it's just a sound from the microphone, just a record, and then we
But then my
reviewed it
question,
as amplitude.
yeah, okay. But my question then, have you pre-processed it or transformed it on frequency domain? And if you didn't do this, why? Maybe there is some motivation behind this analysis of the pure amplitude data in your case. But usually it's like people transform it in frequency domain, like doing some preprocessing.
Yeah, we the only things we did it was just trying to clean up the sound with the different methods. But even after cleaning up, it didn't help very well. Because the sounds were made by the records were made by different doctors in different conditions. That's why if we try to make it ideally clean, then we lose the actual sound. And other methods, if we try to make it 20% cleaner, then there is no change in the results. And but yeah, I appreciate this idea. We should try to analyze it as a frequency domains.
Yeah, it's the kind of classical approach. If you want to clusterize or classify sound, it's, maybe it's worth to try at least to convert to frequencies. Okay, anyway, thank you very much.
Thanks.
Yeah, thank you. Are there any questions from the online? Okay. It seems like we don't have any questions from the Zoom. Any questions offline? No? Okay, so let's thank the Ekaterina again for her talk. And the next, yeah, thank you. The next talk is an application of dynamic graph CNN and ICP for detection and research archaeology sites by Alexander Vakhmintsev, Olga Christodula, Andrei Melnikov, and Matvey Romanov. Dear presenters, are you here? Yes, we see some screen sharing.
Добрый день, уважаемые коллеги. Вот, да, со мной случилась такая достаточно неприятная история. Перед конференцией я заболел, оказалось, что это какой-то редкий вариант коронавируса. Пришлось отменять билеты.
Could I please ask you to? We have an international conference, and like some of the speakers they don't understand Russian. Could you please switch to
Вот как раз-таки одна из проблем, которая возникла, что мне вот главный врач разрешил ограниченное участие в конференции принять. Ну и в том числе вот у нас какие-то теперь в военных госпиталях такие требования, что не разрешили мне делать доклад на английском. Вот если простите, то можно будет в таком формате выступить?
Well, could we? I don't know.
К сожалению, это вот такой был
Yes. Sorry. Yes. Okay. For the. Yes. So. Forbidden to speak English. Yes, by doctor. Yes. Yes. Kind of not clear. Yeah. Unfortunately, we really do. Some of the speakers not understanding Russian. Maybe we could switch it to the end of the talk. So yes, so if we could please then make your presentation then the last one, so the people who are not really prepared to to here for the report in Russian could like stay after, so they could actually like left to other section and stuff, so we couldn't like waste their time. Would this be acceptable for you, please?
То есть далеко не все смогут, да, прослушать, насколько я понял, да? То есть
Да, к сожалению, да, тут не все говорят по-русски. И если можно, давайте мы вас последним поставим, и тогда все
давайте.
интересы будут учтены. Okay, thank you so much for understanding. So I should ask Vladimir Belikov, who is the next. Yeah, could you please stop sharing the screen then? Would ask Vladimir Belikov, who is the next. Oh, we have a second offline. Yeah, could you please have an applause, because yeah, we were thinking about having you offline. So the talk is named "Ensemble Clustering with Heterogeneous Transfer Learning" by Vladimir Belikov, and you have your presentations uploaded, right? Or is it? It's your presentation or it's not? Can please offline presenter stop sharing the presentation? Yeah, just 1 minute. Thank you for coming offline. Maybe you can go to event right now. Yeah, we have some small technical difficulties. So at least from my perspective, I was surprised because I had information. So you will be given a talk online. So yeah, I got false information here. Sorry for that. So maybe that's the reason. So I had this in timetable. Yeah, thank you.
Dear colleagues, let me introduce my presentation on some combination of clustering, ensemble models, and domain adaptation or transfer learning. So, what is transfer learning, or sometimes called domain adaptation? So we have two domains. The first domain is so-called target domain or domain of interest. And besides that, we have some additional information or source domain. For example, we have text in English, and we can use this information to improve classification or clustering of text in German on some related language. There are different kinds of transfer learning, supervised or weakly supervised, depending on the labeling process. So some data may be incompletely labeling or imprecisely labeled, so on. And in this work, we consider so-called heterogeneous transfer learning, and the domain have quite different feature space information. So we have target domain, and it is required to obtain a partition of this data set on some number of clusters. And additional information is source domain, where objects are described in different feature space with different feature dimensionality. So source domain is labeled, and we should perform clustering of target domain. And it is hypothesized that the domains have something common in their structure, some common regularities, and these regularities can be revealed by cluster analysis and used as additional information to improve clustering. What means by improving, we shall discuss later. So we use cluster ensemble methodology when we have a number of clustering results and we combine them to obtain some consensus variant of partitioning. And there are some known works on this problem, but these works have some limitations. For example, they consider common feature spaces, or the time complexity is very hard, of cubic complexity, and is too much for many applications. Or we should have multiple domains, additional domains or source domains. These domains are not easily found in practice. And we propose methods which have four basic stages. The first one is independent analysis of data, so we perform clustering of both source and target domain in parallel or independently. We use lower rank representation of obtained similarity metrics to decrease computational cost. The next stage is extraction of knowledge. We use some supervised classification algorithm and find the classifier for prediction of the elements of co-association matrix in source data, because we know labeling in source data, and transfer them to target data using so-called meta-features. Meta-features are features which describe some common regularities in data structure. For example, number of clusters, or form of clusters, or some characteristics of the form. And they do not depend on initial feature spaces. Then we use the found regularities to predict co-association matrix in target domain and perform, on the last step, final clustering. We construct the partition of target data using the predicted co-association matrix. A few words about ensemble clustering. Here you can see some example. We have several partitions of data obtained by different algorithms or by one algorithm with different initializations or different working parameters and so on. Then we obtain average co-association matrix. Each element is the frequency of for a given pair of objects, a frequency of falling to the same cluster, and then we using this matrix we find a consensus partition using some algorithm which takes this information about similarities in the objects. For example, hierarchical clustering algorithm, or spectral clustering, and so on. This matrix, or co-association matrix, can be represented in a low rank form using rectangular matrices or association matrices, and this gives significant memory savings or computational savings, because it's not necessary to save in memory a large quadratic matrix. For example, million by million is a huge number of elements. The steps of the algorithm are shown here. So we perform independent analysis of source and tangent data using this algorithm, and use spectral clustering for low rank represented matrix of similarities. Now, some previous papers, we have considered some probabilistic properties of cluster ensembles. So if we suppose that there exists some ground truth variable that determines for each pair if it belongs to the same cluster or different clusters, and we can define the conditional probability of classification error, and it is possible to use some regularity assumptions, probabilistic assumptions, to prove that the algorithm, the classification error converges to zero when the size of the sample grows, and other things being equal, diversity in the ensemble gives the smaller error. However, in practice, some or many or all violations or all assumptions can be violated. So we have, for example, some we have not large memory and so on. So for small number of ensemble members, we use additional data, source data, to improve the clustering results. As meta features, first of all, we use frequencies of the assignment of objects into the same clusters or elements of co-association matrices from source and target domain. Then we use meta feature based on silhouette index. It's well established index, internal clustering index, and we define it for each pair of objects and use its additional information. Then we calculate coincidence matrix or co-association matrix and find the decision function or classifier for predicted elements of the matrix dependent on the meta features used. We can use machine learning algorithms such as random forest, support vector machine, or artificial neural networks, and so on. Some well-known techniques can be used to evaluate the performance of the quality of the classifier or find important meta features. And then it's possible to transfer the found classifier to the target domain for predicting the association matrix. And the final step is clustering based on the predicted matrix. But there are some problems that this matrix cannot be directly used for clustering because some metric properties can be violated for this matrix. So we apply an approximate solution. We start from some initial partition of data, of target data, and then migrate different points to another clusters to get the best improvement of the criterion. This is the steps of the algorithm. So they perform 3 or 4 stages of the algorithm: independent analysis, finding meta features, finding classifier, and transferring the classifier from source to target domain, and find final partition of the data. Unfortunately, time and memory complexity of quadratic order, because we need to consider all pairs of elements, but it can be improved because we can use some methods such as stochastic gradient, and using this method, it's possible to consider only part of data, not all data pairs, pairs of data points by some subsamples, and this can reduce memory. We have performed experiments with some data sets, with artificial data sets using Monte Carlo simulation with data. So we generate data multiple times, then perform clustering and define the quality of the result. And then we can average the results of all experiments. Here are shown some examples of generated data. Use k-means as a basic algorithm, and random forest and support vector machine for classification and knowledge transfer. The next example is more real based, but I think it's more, also some illustration of the method. So we used a MNIST data set of handwritten digits and perform classification using feed-forward artificial network. So we use some batch normalization, stochastic gradient descent, and in addition to the above mentioned meta features, we use also additional meta features such as normalized pairwise distances between objects and average distances to closest centroids. To evaluate the quality of clustering, we applied external cluster validity index. There are different types of external indices. For example, adjusted random index. It estimates the degree of similarity between two partitions. The first one is obtained, and the second is the ground truth partition. And this index is corrected for chance estimate of probability of covariant assignments of object pairs to same or different clusters. The formula is given here. The more closer to 1, the better is the matching between the two partitions, and index close to 0 indicates nearly random correspondence. And these are the results of experiments. First of all, for artificial data, it can be seen that the proposed algorithm gives some improvement of quality, clustering quality. And this is the example of decision boundary obtained with support vector machine algorithm. So it can be seen that silhouette based index is also gives some information on the decision boundary. Both of the features are useful for classification, but of course, causation matrix base is more important. And these are the examples, results of experiments for real data on this database. So it can be seen that this algorithm also gives some improvement, not ideal, of course, but some improvement of clustering quality the average best result and worst result. And here is given an example of clusters obtained. You can see that the first cluster includes correct assignments, and there are some mistakes in the second cluster. And this is a conclusion, so we propose some modification of ensemble clustering based on transfer learning. And of course, this is not ideal algorithm, and some future works are planned. For example, we are going to, me and my students from Novosibirsk State University, other types of meta features and application of the method in different fields, for example, for text document analysis. So this is all. Thank you for attention.
Thank you for an interesting talk. Any questions from the audience? Well, if I may allow, I myself have one question. So, to the best of my understanding, and please give me the rope here, so maybe I didn't understand correctly. So, your work adds another layer on top of classification, clusterization to solve this problem. So you're kind of doing it on the meta level. So my question is actually about the interpretation, explainability of the features, because when you're adding more and more, even if your underlying classifier is kind of, you know, interpretable, like let's say linear classifier, you can like interpret this, like is this interpretability passed through your algorithm? What do you think? Could some approaches in this direction help the ones who want to do it?
Yes, I think it's possible to evaluate the importance of the features using some methods such as random forest or so on. Yes, I think it's possible, if I correctly understood you.
Okay, so you are proposing to make interpretability on the produced features, right? Yes. Okay, thank you. Any other questions? Okay, maybe the second question from myself is related to the amount of hyperparameters you have, because you're having, like, let's say, from my understanding, is kind of really complicated data analysis and feature engineering on top of it. So I'm interested in, like, let's say, how many hyperparameters does your, let's say, meta layer add to the simpler parts? Yeah. My question is.
If I correctly understood, there are, I think, about a dozen of hyperparameters or meta features used in different literature or work, but we tried to use some of them, but the effect was pretty small.
Okay, and I assume there are also no online question, because actually selected people are doing from Zoom, but there may be some from the YouTube translation. So thanks. Let's thank the speaker again. Thank you so much. And now our next talk should be an online talk. The work is named Metamorphic Testing for Recommender System by Sofia Yakusheva and Anton Hritankov. Yep, sorry if I misspelled something of that. Let us just switch to the Zoom translation now. Are the speakers here?
Oh, yes, I'm here.
Great.
Can you hear me?
Yes, we can hear you super clearly. Could you please share the screen?
Just a second. So, hello everyone. Can I start my presentation?
Just a second.
Okay.
So offline speakers, offline listeners would also enjoy this. Yes, okay, please start. You have 18 minutes.
Okay, thank you very much. So hello everyone. I'm very happy to see all of you today. I'm very happy that I can present our work to you today. So my name is Sofia Yakusheva. I am assistant at the Department of Algorithms and Programming Technologies at Moscow Institute of Physics and Technology. And Anton Kritankov is my supervisor. So today we will talk about metamorphic testing for recommender systems. So recommender systems is a popular topic today, but the problem is that they can badly hurt users if we don't test them carefully. So we should test them as carefully as we can. But we face a lot of problems, for example, lack of test data or needs for human judgment. All of these problems have a very high cost, so we can't use humans a lot. Another problem is the stochastic nature of recommender systems, because not all the methods can be applied to these systems. And the last but not the least, historical problem. So what is that? Historical is a partial function to the set of true.
Sorry, Sophie, sorry to interrupt you. Could you please, I think we see it on your screen, so that's the part of the Zoom on your side, which is covering the part of the slide on the right.
Sorry.
Yeah, could you please make it?
Is it better?
Yes, now much better. So thank you so much.
Sorry, I'm very sorry. So what is the historical problem? As I said, historical is a partial function. In simple words, this function says us if the test is passed or not. The simplest example is if we have, for example, right answer for the test, we can just compare the answer of the program and the right answer and say if the test is passed or not. But the historical problem says that sometimes it's computationally expensive or even impossible to get a historical for some problems. And testing recommender systems is such a problem that in general don't have historical. But fortunately, there are some testings to test such problem. And one of them is metamorphic testing. The key idea of this method is not to check every single output. Instead of that, we have many inputs of the program and many corresponding outputs. Our task is to check if there is some relation between these inputs and outputs. The smallest example is, for example, if we have a database and we request this database. For the first request, we use the filter A, and the second, we use filter A and B. So the answer for the second request will be a subset of the answer for the first request. And we don't check if the first or second answer is correct themselves. We just check the relation between them. So we tried to apply this method for testing stochastic systems. I should say that some articles on metamorphic testing use statistic methods, but they use only criteria and do not pay much attention to the general overview of this stochastic testing. So we make some generalization and propose stochastic metamorphic relation. So what is that? Classic metamorphic relation is just a deterministic function with many inputs to the set of 0 and 1. So we consider this function as a composition of sampling procedure and function of determination. So the sampling procedure is stochastic, and function of determination is something like statistic criteria, maybe. In this case, we will have much more information about our system than if we use only classic metamorphic relation. We formulate some requirements for recommender systems in general. You can see all these requirements. It's technical reproducibility, ability to learn, response to changes, comparison on different models, homogeneity of parameters, some asymptotics, individual features of algorithms, and the response to linear transformations of distribution parameters. You can see somewhere the word banded. It's because we apply our method to the multi-armed banded problem. Now, multi-armed banded is a model of slot machine with several arms. If the user selects some arms, he can gain a reward. And the task of the user is to maximize this reward. And this model used in some services like Amazon or Spotify, when we have a list of options and we want to get it for user, but we can get only a short sublist of this list. So we propose some metamorphic relations for multi-armed banded problem. We propose 6, but I want to show you only 2 of them. The other 4 can be easily derived from the requirements, but these 2 are more interesting, I think. The requirement for the first was assumption about homogeneity of parameters. That means that if we permute banded sums, the reward should remain the same. So that means that the algorithm do not pay much more attention to the number of the arm. And I think that's a very important property of the algorithm. And the second is comparison of less and more profitable bandits. So if we apply some linear transformation to the probabilities of getting reward, our reward will change correspondingly. So it will be bigger. But for optimal algorithm, this reward can be get with linear transformations that we apply to our probabilities. I hope I explained this okay. So we test a lot of algorithms of bandit. Some of them were stationary, some of them were not stationary. For example, FDSWTS is non-stationary. And for comparison, we use random algorithm and optimal algorithm. And we use a multi-armed bandit model with Bernoulli distributions on each arms. And these distributions were stationary in time. So we have some interesting results. For example, we compare different parameters for AIST'2023 algorithm. And we notice that for some of these parameters, these algorithms work a lot worse than for others. So our stochastic metamorphic relations are useful for detect bad algorithm parameters. For FD'2023, we notice that permutation of arms have a lot of impact, and it is not very well. There are some examples of failures that we detected. This picture shows failure in configuration. So our metamorphic relation was applied only for the first algorithm in the bench of algorithms, and the other were the same. So it was our mistake, and we fortunately correct this. Other example is for configuration fails too. In our project, the configuration files were a bit complicated. So this picture shows almost identical experiments that were supposed to be completely different. And it is another example. And the most interesting result, we apply the 6-hour SMR for algorithm. And this SMR was about linear transformation of probabilities. So we expect that if we apply this linear transformation for the first experiment, we will get the same reward as for the second experiment where the probabilities were transformed already. But we don't have such a result. These values were different. For random algorithms, these values were the same, but for the others, this was completely different. And you can see at the picture for the purple line that these algorithms don't even multiply reward like the others. This was FDSWTS algorithm, which is non-stationary. And there we use our stochastic part of metamorphic relations to analyze the error. So you can see that for the random algorithm, this difference was almost 0. And for X3, it is not that big, but still not 0. For Thompson sampling algorithm, this difference is less during the time. And for the X3, it's rising, I think. And for FDSWTS algorithm, this difference is significantly bigger than 0 and much more bigger than for the other algorithms. So we consider this result as an individual feature for FDSWTS algorithm, because the model which is used in this algorithm is more complex than for us. So in conclusion, we consider the problem of recommender system verification. We propose some stochastic metamorphic relations, formulate requirements for recommender systems in general, derive stochastic metamorphic relations for multi-independent problem, test the problem, and find some failures. So a code of our experiments is acceptable in the internet. You can see it via links on the screen. And a small addition from the experiments that we don't include to our paper. We test some bandits, contextual bandits, which use additional information of context. For example, the season or the time of day or the number of day in the week. And we consider two algorithms, C2UCB and LinUCB. We test them on the constant context, and we discover then LinUCB algorithm learn very well, and C2UCB doesn't learn at all. And we make a conclusion that C2UCB algorithm is much more focused on the context than the LinUCB algorithm. So our stochastic metamorphic relations are useful for discovering such thing. So thank you for your attention. My talk is over. I will be happy to answer your questions.
Dear Sophia, thanks for your interesting talk, and another additional thanks from me, the chair. So you just made it in 12 minutes, so we will be just on time, unlike the German trains. So do we have any questions from the audience? I have a question about this approach. I'm actually interested in some, so to the best of my understanding, you propose another way of doing, let's say, A/B testing in a way. So, and you propose, yes, another approach to the multi-element bandits problem. I am curious whether you thought about of the combined strategy of like combining your algorithm with the other known algorithms in the field, such as epsilon greedy or Thompson sampling, whether it could yield better results, whether the combination of the algorithms work, for example, like switching from one mode of decision making on the test to another. Thanks.
Metamorphic testing is more about offline testing of the algorithm. When we test just models or our realization, it's more about of verification of requirements and not the A/B testing. But idea of this SMRs is quite the same because we use some statistics. For future of our work, we will try to make some compositions of these metamorphic relations for complex system. So we can propose some relation for the company to the system, but for the whole system, it's much more complex, hard, complicated. I don't know. So this is a vector of our future work. But about A/B testing, so maybe it's a good idea, but unfortunately for A/B testing, we should use users or bots. And this is quite expensive. For our small research, we just make some experiments and, and have a result. But your idea is very interesting. Thank you.
Yeah, thank you. We have a question from the audience.
Thank you for the talk. Am I right that you tested everything on Bernoulli rewards, the model?
At this stage, yes. Just band it with stationary Bernoulli reward. This reward is 0 or 1 at every step.
Yes, I see. The question is, do you plan to like extend it to different models of reward, like distributions?
No, of course, yeah. We plan this.
Good. Thank you.
Any other questions? Yeah, well, it seems like we're out of question now, but we still have some additional time. So let's thank the speaker again. And
thank you very much for your attention.
Yeah, thank you very much. And our next speaker our next talk is titled Application of Multimodal Machine Learning for Image Recommendation Systems by Mikhail Fanyakov, Anatoly Berdukov, and Ilya Makarov. Are the presenters here?
One moment. Are you here to me?
Yes, we can hear you clearly.
One moment. Are you see?
Yes, if you could just, yes, wow, now it's just great. Thank you. You have 18 minutes.
One moment. One moment. Good morning. My name is Mikhail Fanikov, and I'm graduate of High School of Economics of the program Master of Data Science. My supervisor is Anatoly Berdukov. The topic of my paper is application of multimodal machine learning for image recommendation system. We are living in the era of an abundance of information. It can be very difficult to find the necessary information or some important content. People use online stores, e-commerce platforms, marketplace, but they need to systemize all this information. People start to upload the information, images for everything they preferred. It can be product, a landscape, some funny photo. So images became the basis of the development of recommendations and main data types, and one of the main data types of recommender system. What is the recommender system? It's a class of machine learning algorithm that use data to help predict and find what people are looking for among an exponentially growing number of options. This system have one basic goal: to solve the problem of information overload, making it easier for the users to search the goods. However, these traditional recommendation algorithms are not perfect. There are many types of data that can be used for recommendation purpose, additional purpose of the goods, descriptive text of the goods, or some metrics which we can obtain. These properties or characteristics are called multimodal information, and the system that use the information are called multimodal. What's multimodal? Multimodal, the application of multiple approach within one medium. What's multimodal data? Multimodal data is data with different types, such as different embeddings, text descriptions, various types of metrics. It allows us to implement different features which simplify the training process and obtaining high quality recommendation. For building my recommender system, we need some data set for learning our model. I use data set with images from Yandex, and it has the following structure. Initial image. It can be a completely random image. Candidate image, the picture which is recommended or isn't recommended for the initial image. And of course, the target is the binomial target of the pair of the images. 1, the image are similar, and 0, the image are not similar. So more than 75,000 pairs have target 1, and about 30,000 have the target 0. Thus, the data has imbalanced structure and needs some preprocessing. For building multimodal system, we should use different features for each images. An important part of our recommender system is a description text of the picture. I have passed it from Yandex picture using the beautiful SubPython library. This is the simplest and the most accessible method. I obtained the text in different language for each picture. I processed all images using clip. It's a very useful technique for image embeddings with a lot of models. For text processing, I used another technique, which is called BERT. I used some multilingual model in 104 languages. The next step of preprocessing data is metrics counting. For each pair of images and text, I use 2 metrics to count pair distances between two clips vectors for images and 2 BERT vectors for text, cosine similarity, and the square Euclidean. I chose from 4 models. It's decision tree classifier, random forest classifier, XGBoost classifier, and CutBoost classifier with queries and without queries. Queries is groups for candidate images. It is equal to number of initial images. We see that the CutBoost classifier has the best results. So our dataset has the following structure. It's 10 features, 2 embedding features of clip dimensions, 2 embedding features for BERT dimensions, 4 numerical features for metrics, 1 feature is the binomial target variable, and 1 feature is a query, categorical feature, the number of the related image. Here we see that the optimal learning rate is 0.001. For my multimodal recommender system, I will the model based on CutBoost algorithm. It is an algorithm for gradient boosting on decision trees, which was developed by Yandex engineers. In this algorithm, I use CatBoost classifier package, the classificator of the CatBoost algorithm, because my dataset has only two target variables, 0 and 1. For model constructing, my data needs in some preprocessing. Matrix feature was scaled using standard scale method. I learned my model with following hyperparameters. Iterations is 2000. It is optimal number of iteration for learning model with such data. Early stop rounds is 20. The algorithm stops in training if the parameter dictate. Learning rate is 0.001. I need a small gradient step size. It helps to learn my model more accurately. Max depth is 6. It is the optimal depth of the trees for classification model. And scale post wide, 2.64. As I have imbalanced data, I use the parameter with this value, which is equal to ratio of majority class to minority class. Model result. As a loss function, I use logarithmic loss function. This is matrix of evaluating the performance by binary classification model. As a custom metric, I used AUG, area under curve. AUG is an effective method to visualize the performance of the model. After the learning model, we have the AUG is equal to 0.83. It says the probability of prediction positive class is higher than the prediction of negative class. The loss, a function log loss of the model is 0.29. However, I will use predicted probabilities of positive classes output of our model. It will help us to range the result of our future experiment. Performed matrix shows the quality of ranging as we will range our images. Its indicator is 0.77. One moment, sorry. One moment. So we need some experiment with our data. For the experiment, the data needs in another preprocessing. What the data preprocessing is? We set 3 experiments using only clip embeddings, using only BERT embeddings, and using our model with clip and BERT embeddings. For experiments, my dataset needs some preparation. I divided it using package k-means from the sklearn library. This is the most popular clusterization method. I separated my dataset into 1000 clusters according to clip and BERT vector. Also, I have obtained the cluster distance for each cluster of each image. Then, using this data, I counted 3 nearest clusters for each images, and I have separated my dataset into pairs according to belonging in 3 clusters. For each pair, I counted its cosine similarity and Euclidean distance for clip and BERT vectors. So I have dataset with the following structure: the clip vector for related image, the clip vector for candidate image, the BERT vector for related image, the BERT vector for candidate image, the cosine similarity between 2 clip vectors, the cosine similarity between 2 BERT vectors, the Euclidean distance between clip vectors, and the Euclidean distance to BERT vectors. So my experiments, we group a certain number of candidates with the higher for cosine similarity and with the lower for Euclidean distance matrix of clip vectors, BERT vectors, or probabilities of the positive class for each image. In this case, the number is equal to 5. For CatBoost model and clip vector, the system selected the correct images without any mistakes. So the accuracy here is equal to 1. For the BERT embedding, the system has 2 mistakes in the first and the second images. And for BERT vector, then the image for the correct images for the BERT vector, the system made 2 mistakes in the first and the second images. Its accuracy is 0.4. The second experiment, CatBoost model has mistakes in the last image, the accuracy is 0.8. Clip model has mistakes in the fourth and the fifth image. The accuracy is 0.6. BERT model has no correct images, of course. The accuracy is 0. The experiment number 3, CatBoost model, Clip model, and BERT model has no mistakes, so the accuracy is 1. The experiment number 4, CatBoost models has no mistakes. The accuracy is 1. Clip model has mistake in the second image. The accuracy is 0.8. BERT model has mistakes in the third, fourth, and fifth image. The accuracy is 0.4. Experiment number 5, for the CatBoost model and clip vector, the system selected the correct images without any mistakes. So the accuracy here is equal to 1. For the BERT embedding, the system has mistakes in the third image. Its accuracy is 0.8. So I also analyzed 2025 images and obtained the following result. For CatBoost model, the average accuracy is more than 0.8. The accuracy of clip vector is less than 0.8, and the accuracy of BERT vector is less than 0.5. Also, I have experiment for Flickr image dataset. The Flickr image dataset is simpler than the Yandex dataset. So in the experiment 1, all models have accuracy equal to 1. The second equal to 1 too, and the third experiment. There are no mistakes for the CatBoost model. For clip vector, there is one mistake in the fourth image. So the accuracy is 0.8 for BERT embedding. The system has mistake in the third, fourth, and fifth image. The accuracy is 0.4. I have analyzed 50 images and get the following result. For CatBoost model, the average accuracy is more than 0.97. For the clip vector, 0.95, and for the BERT vectors is less than 0.85. So this is an unique multimodal recommender system for images. Model is based not only image features, but also text features such as embedding and metrics. However, there are additional training for BERT model and build more perfect vectors. Looking for another NLP model is getting additional text for pictures and finding additional features. So the multimodal needs to improve constantly. Perfect, there will be more researchers for the topics, and this system has a wonderful future. Thank you for attention.
Mikhail, thank you for your talk. Extra points for making it short and precise. We have quite a few questions on the audience. Yes, let's start with you.
Thank you for your talk. I just want to clarify, you mentioned that for the CatBoost algorithm, your depth was 6, and you mentioned that it was optimal one. Can you please explain how did you determine that it was the optimal one? Did you perform some grid search, or did you fix the over parameters and just run through the depth only, or something else? Thank you.
Would you like to please repeat your question?
Yes, in simple words, why did you choose your depth to be 6 in CatBoost model?
The depth to be 6 is the optimal depth of the many decision trees algorithm. It's not its optimal depth. It's not need the depth more than 6, and the less depth is not perfect.
Yep. Thank you. Another question?
Thank you, Mikhail. Thank you for the talk. If you can open the slides, the examples were
1 moment.
Very interesting. It seems that it seems that you find using the query, you find similar images. Right?
One moment.
Yeah, with pictures. So you consider this as the criteria for quality. The accuracy here is the similar image is the better, right?
Yes, of course. The similar image, the first column is the related image, yes. And
the
5
question
all.
is, okay, I have 2 questions. Why is that actually a recommender system? For me, it looks like a similarity search, looking for similar images or something like this. Can you comment on this? And the second question, you know, if you, in practice, if you recommend to users all the images that are similar, that they like, your system will get positive feedback and will degrade the quality. I mean, if you show nice cats to a user and user likes it, next time you show more nice cats, and after several iterations, user will get only the nice cats pictures in his recommender system. How your approach will solve such problem? Yeah, and the first one is just why you call it the recommender system if it is just a similarity search.
Why as I say that my this recommender system is based on clip and BERT embeddings. So the recommender system is using these features, of course, and recommend system according to main 2 parts: clip embeddings and BERT embeddings. So the future work of this recommender system is to learn the BERT model. For the result show that the BERT model have the less accuracy, the smaller accuracy than the clip and the cut boost model. Okay. And the BERT model will be more advanced. For learning the BERT model is the best way to improve this recommended system, of course.
Okay. I didn't get if it is the answer, but okay. But what about the degradation of the model if you, in practice, if you recommend the same images to the user all the time?
Degradation.
Yeah.
Degradation, as I said, the model has a good future. Has a wonderful future.
Wonderful future. Okay.
Wonderful future. When the model will be learned regularly with BERT model, and in the future, it can be better to use ChatGPT model instead BERT, or the more complex model than BERT, of course.
Yeah. Okay. Thank you very much. Maybe other question.
Any other questions from the audience? Maybe I would just also like to note on this very work. So it's kind of this multimodal approaches, they're kind of new territory, and one of the reviewers also had this question: why is the recommender system if it's like just the similarity system? And it's really again hard to account for all the problems and practical applications of the newer approach, but I think we could all agree so the multimodal approaches, they in this work they yield better results and should be considered when building this approach as a part of the recommender system. Yes, I guess we have no questions from the audience, so let's thank the speaker again. So dear online participants, unfortunately one of our speakers is unable to deliver yes Mikhail.
Yes.
Yeah, unfortunately our speaker right now is unable to deliver the report in English, we live in the dark and weird times. And unfortunately, we also have some responsibilities as international conference. So like in terms of staying international, the next report will be off the record, but we will give a chance to disseminate the knowledge between acknowledged speakers. So once again, unfortunately, next report will be on Russian only. Yes, we would like to thank our international guests. Just a second, we need to figure out how to stop the recording. If we could.
Вы видите, да, презентацию?
Я скажу, когда можно будет начинать. Сейчас, простите, пару минут буквально. Sorry, we have again some technical difficulties. It's an extreme situation to be in.
Стриминг не получится, мне Мария написала.
Okay. So it's not really possible.
Но все равно
Да. Окей. Все, у нас следующий доклад будет по-русски. Извинения всем международным коллегам, которые не понимают русский язык. И доклад называется Application of Dynamic Graph CNN and FICP for Detection and Research Archaeology Sites. И Александр будет сейчас нам докладывать. Спасибо.
Здравствуйте еще раз, коллеги. Приношу извинения за такую вот ситуацию, в которую я попал от себя лично и вот от всего нашего научного коллектива. Я представляю доклад применения динамического графа сверточной нейронной сети и комбинированного итеративного алгоритма ближайших точек для вот таких прикладных задач, как детекция и исследование археологических памятников. Надо сказать, что результаты, которые мы получили, они связаны с выполнением нашим коллективом гранта Российского научного фонда, который мы получили в этом году. Вот в результате выполнения этого проекта мы должны решить две научные задачи. Во-первых, создать методы для детекции археологических памятников. И вторая группа методов – это для исследования археологических памятников. Если говорить про саму математическую основу этих методов, то они основаны на методах машинного обучения, методах геофизики и картографирования. Надо сказать, что достаточно недавно археологи практически занимались детекцией археологических памятников вручную. Ну, например, они использовали для решения данной задачи данные аэрофотоснимков и космоснимков. Вот в левой части слайда мы можем видеть как раз-таки аэрофотоснимок, ну а в правой части результаты его дешифрирования. Ну вот в последние, наверное, 15 лет методы точных наук получили достаточно широкое распространение в археологии, ну и в том числе методы геофизики и машинного обучения. Достаточно много работ в этом направлении ведется. Вот я, пожалуй, остановлусь только на одной работе, которая была проведена коллективом немецких археологов. Они как раз-таки исследовали поселения Средневековья. Но эти поселения из себя представляли на сегодняшний день некоторые курганы и занимались детекцией вот этих поселений по данным датчиков глубины, которые они получали с камер глубины, либо времяпролетных камер, которые были установлены на беспилотных летательных аппаратах. Ну, вот здесь можно видеть некоторую визуализацию, как выглядят данные курганы. Нас эта работа заинтересовала по той простой причине, что археологические памятники, которые находятся на территории Южного Урала, И вот эти курганы, которые находятся на территории Германии, они имеют схожие признаки дешифрирования. Ну вот немножко расскажу о том, что из себя представляют памятники, археологические памятники на территории Южного Урала. Большинство из них относятся к так называемому бронзовому веку и связаны с миграциями индоевропейцев на территорию Урала и юго-западной Сибири. Там они организовали целый пласт городов, многие из которых находятся в рамках так называемой синташтинской культуры по названию реки Синташта. Но самым известным памятником этого комплекса является город Аркаим. Ну а на самом деле на сегодняшний день выделено порядка 20 подобных укрепленных городищ помимо Аркаима. В 80-х годах прошлого века профессором Здановичем был опубликован такой фундаментальный труд, в котором он исследовал все эти города, ну и фактически там же были определены признаки дешифрирования этих археологических памятников, которые мы использовали в нашем проекте. Нами было выделено 9 классов интереса, 5 из которых обозначены как К1, К5. Это классы курганов, которые имеют различные текстуры, то есть это какая-то распаханная поверхность, либо какая-то каменистая поверхность. 2 объекта – это могильники. Одни из них относят к эпохе как раз бронзового века, а другие могильники связаны с более поздним освоением этих территорий, ну, в частности, с бронзовым веком. И также поселения, укрепленные и неукрепленные, соответственно, классы P1 и P2. Ну вот на данном слайде представлены некоторые признаки дешифрирования. На самом деле их достаточно много. И многие из них, в принципе, конечно, не удастся использоваться в методах машинного обучения, такие как, допустим, размер объекта, либо там взаимное расположение объектов относительно друг друга. Но, тем не менее, вот такие признаки существуют. Если немецкие археологи в своей работе использовали, собственно говоря, только один источник данных, то мы в своей работе опираемся на 6 источников информации. Первый источник – это, собственно говоря, материалы аэрофотосъемки, которые были произведены еще в прошлом веке, когда не было хозяйственного освоения данных территорий, и они имеют очень большое значение, поскольку на них многие эти археологические памятники еще видны. После того, как там была распахана пашня, конечно же, исследовать эти объекты становится значительно сложнее. Второй источник – это данные дистанционного зондирования Земли. Мы используем такие данные со спутников Sentinel, Landcast, Resource-P и Canopus-B. Надо сказать, что у нас собралась достаточно большая коллекция таких снимков за достаточно продолжительный период. Это несколько сотен снимок. И что очень важно, что эти снимки с высоким пространственным разрешением, то есть до 0,7 метров на 1 пиксель. Нами были проведены также некоторые исследования с помощью тахиметрических датчиков, ну, в частности, датчика Trimble. И было построено порядка 40 моделей, которые описывают в виде облака точек вот эти поселения бронзового века на территории Южного Урала. Существовали и другие ортофотопланы, которые археологи получали с 2006 года по этим участкам, но они также были использованы в проекте. Кроме того, достаточно интересный источник, с которым вот мы начали работать только в этом году, и здесь коллеги из ОРАН Института геофизики пришли нам на помощь и выполнили с помощью прибора АМП-14 магнитометрическую съемку 3 поселений: степное, верхнеуральское и левобережное. Ну а также мы используем данные глубины. Вот в этом году на 2 поселениях мы засняли с помощью беспилотника и камеры глубины эти поселения и получили их подробные трехмерные карты. Все источники данных можно поделить принципиально на 2 типа. Это двумерные данные и трехмерные данные. Для обработки двухмерных данных мы используем остаточные нейронные сети. то есть сети ResNet. В общем-то, идем по пути немецких коллег. А вот для анализа трехмерных данных нами был предложен и опубликован, в том числе в результатах этого доклада, новый метод. Мы его называем методом DigiCNN со звездочкой, либо у него есть еще второе название, которое мы дали, MGCNN, так называемый мультимодальный граф сверточной нейронной сети. Надо сказать, что методы для классификации и сегментации трехмерных моделей данных бывают разные. Условно их можно поделить на две большие группы. Это прямые и непрямые методы. Но в первую очередь интересуют, конечно, прямые методы, яркими представителями которых являются методы DigiCNN и RGCNN. Но для решения поставленной нашей задачи данные методы не совсем хорошо подходят. И это связано с их недостатками. Вот первый из таких недостатков – это ограничение по размерности данных. Эти методы хорошо работают в промышленном дизайне, когда размерность задачи – это несколько тысяч точек, ну где-то до 10 тысяч точек. Если точек уже становится больше, а у нас вот порядок это бывает 13 тысяч, 22 тысячи в облаке, то эти методы уже не очень хорошо работают. Вторая проблема связана с тем, какую форму имеют трехмерные модели. Вот эти методы хорошо работают для выпуклых моделей данных. Археологические памятники бронзового века, они расположены в степи, в лес или какой-то даже запустыненной территории. Поэтому вот визуально эти городища представляют из себя достаточно выпуклые объекты. Есть также проблемы, связанные с тем, что вот эти методы в основном используют одну либо две модальности, но информацию о цвете они, как правило, вообще не используют. Ну и вот для преодоления этих недостатков нами была предложена новая архитектура, которую мы назвали динамически взвешенный мультимодальный сверточный граф нейронной сети. Он имеет входные данные, которые содержат 12 признаков. Это, собственно говоря, сами координаты точек, это нормали к точкам, это цветовые признаки. И также впоследствии этот набор добавляется еще нормализованными координатами, поэтому на каждую точку приходится 12 признаков. Ну, также добавлю, поскольку RGB это все-таки не независимые признаки, то мы в нашей работе осуществляем преобразование RGB в HSV, ну и таким образом нам тоже удается повысить качество решения задачи сегментации. Вот суть нашей концепции заключается в том, что мы представляем, собственно говоря, наше облако точек в виде взвешенного динамического графа, который описывается с помощью матрицы Киргофа. При этом построение вот этой матрицы Киргофа оно происходит в каждом сверточном слое нашей нейронной сети. Ну и вот в области вот таких графов, динамических пространственных графов, вот эти сверточные слои принято называть слоями H-involution. Помимо всего этого, вот в эту архитектуру был добавлен у нас свой метрический классификатор, который основан на двух многослойных нейронных сетях и одном классификаторе с радиально-базисными функциями. Вот на данном слайде представлен алгоритм, который иллюстрирует основные шаги работы этого алгоритма. Добавлю, что, конечно, существует точное решение задачи спектральной фильтрации, но нам еще важно, чтобы была достаточно высокая производительность. Поэтому мы используем полиномы Чебышева третьего порядка с коэффициентами 6, 5 и 3 для аппроксимации спектральной фильтрации. Ну и вот основной цикл обработки, он в нашем графе сверточной нейронной сети состоит из следующих этапов. Это построение матрицы Киргофа, нормализация компонент этой матрицы, аппроксимация сигнала графа с помощью полинома Чебышева, ну в данном случае третьего порядка, выполнение, собственно говоря, операции свертки на графе, ну и формирование выхода. Ну, далее здесь есть некоторые нюансы с конкатенацией локальных и глобальных признаков, ну и вот генерируется итоговый выход тоже в виде радиальных базисных функций. Также на что следует обратить внимание. Вот здесь в архитектуру был добавлен еще один слой предварительной обработки, который делает повышающую дискретизацию облака точек. Но для чего это, собственно говоря, делается? Потому что, как правило, сканеры глубины, они дают данные достаточно зашумленные, неравномерные, что самым негативным образом сказывается на качестве сегментации. И вот мы с помощью метода КНН добавляем по 3 точки в каждой точке, в результате вот получаем плотное такое однородное равномерное облако точек. Ну и здесь тоже можно увидеть, что у нас есть в нашей сверточной нейронной сети 2 выхода. Первый выход, он решает у нас задачу классификации объектов, ну то есть в глобальном смысле, то есть какой из объектов изображен на картинке. Ну а второй выход сверточной нейронной сети связан с решением задачи сегментации данных. Теперь немножко поговорим о том, какая используется функция потерь в нашем графе. Но по большому счету эта функция представляет из себя мультиклассовую кросс-энтропию, но в нее вот добавлен еще второй такой вспомогательный параметр, который связан с гладкостью сигнала в графе. И этот параметр позволяет нам делать, собственно говоря, объекты смежных точек в облаке более похожими. Еще остановимся на одном моменте. То есть вот эти облака точек, трехмерные данные, они могут быть получены тоже разными способами. То есть мы можем взять тахиометрический датчик, ну, поскольку это достаточно ровная поверхность, мы можем получить сразу всю модель нашего археологического памятника за одну съемку. Если же мы уже будем использовать какой-то лидар, установленный на беспилотнике, то у нас так уже не получится. И для того, чтобы снять археологический памятник, нам потребуется несколько снимков или точек. То же самое можно сказать, когда поверхность какая-то неровная, да, то есть холмистая. И вот в этих случаях, для того, чтобы сопоставить данные с разных ракурсов, в компьютерном зрении решается вот такая задача, как регистрация данных. Нами достаточно давно для решения другой задачи, одновременной навигации и картографирования, был предложен новый алгоритм. Мы его называем комбинированный итеративный алгоритм ближайших точек. И вот этот алгоритм был применен в том числе в рамках вот этого исследования, которое я вам сейчас рассказываю, для регистрации данных об археологических памятниках. Но остановлюсь только на основных 2 свойствах этого алгоритма. Этот алгоритм использует помимо облаков точек данные об особых точек для решения 2 проблем вот этого итеративного алгоритма ближайших точек. Первая из проблем связана с выбором начального значения матрицы поворота и вектора переноса. Ну вот как раз таки мы решаем вначале регистрацию относительно визуальных данных, подбираем какие-то параметры, ну и таким образом нам удается получить вот эти начальные значения. И это уже становится намного лучше, нежели чем подбирать эти значения R и T каким-то эмпирическим путем. Ну и второе, как вы видите, из вида функционала, этот функционал содержит 2 слагаемых, то есть мы, по сути дела, выполняем совместное решение задачи относительно визуальных признаков и трехмерных данных. В работе были проведены некоторые эксперименты, так называемых контролируемых условиях и в неконтролируемых условиях. Под неконтролируемыми условиями мы понимаем различные шумы матричных приемников, неравномерное освещение и так далее. Ну вот мы видим, что наш алгоритм, он здесь обозначен такой линией пунктирной, он имеет некоторые преимущества по сравнению с методами регистрации ICP, известными такими как ICP с метрикой point-to-point, point-to-point с экстраполяцией и с метрикой point-to-plane, точка плоскости. Теперь давайте немного поговорим о компьютерном моделировании. Ну вот, если говорить про цифровые модели, ортофотопланы, которые получаются при съемке с беспилотника, то вот они выглядят каким-то таким образом. Как я уже говорил, перед нами в исследовании стоит принципиальные 2 задачи. Первая задача связана с детекцией археологического памятника с помощью остаточной нейронной сети. То есть нам важно, в принципе, определить место, что что здесь может быть, в принципе, памятник, но не обязательно он может быть. Вот как раз-таки красным светом здесь нейронная сеть обнаружила потенциальный археологический памятник. Ну, вот другой снимок. Здесь вы видите тоже два поселения, укрепленных, выделено предположительно, и курганы. Но если говорить про курганы, конечно, здесь может быть много ошибок, ну, что покажут потом результаты компьютерного моделирования. Вот после того, как такой объект был детектирован, мы можем выделить вот эту зону интереса. И вот в этой зоне интереса у нас находится предполагаемый объект. И уже, собственно говоря, для этой зоны интереса проводятся различные методы исследования, в том числе с привлечением методов геофизики. Вот в этом
Александр,
году...
я
Да.
дико извиняюсь, мы немножко убиваемся из времени. Скажите, сколько вам еще нужно минут,
Ну,
чтобы
давайте я за
закончить?
5 минут тогда закончу, и все тогда коротко.
Меньше, тем лучше. Спасибо.
Спасибо большое. В этом году были проведены вот такие у нас полевые работы. Мы выезжали вот на новое городище Верхнеуральское. Ну, надо сказать, что вообще укрепленных поселений всего было открыто 22 до сегодняшнего года. И вот в этом году удалось открыть, вот в том числе с применением вот таких методов, 2 новых укрепленных поселения, вот, которые мы сейчас взялись изучать. Одно из них – это поселение Верхнеуральское. Ну вот здесь как раз-таки наложены данные глубины на этот снимок. Ну и вот, собственно говоря, цифровая трехмерная модель, снятая с датчика глубины, она выглядит вот таким образом. Вот мы видим здесь этот археологический памятник. Это вот соответствующие аэрофотоснимки этого памятника в разном качестве, получены еще вот в прошлых годах, в 50-х, 60-х годах прошлого века. Ну, а это результаты магнитометрической съемки. Мы также планируем, собственно говоря, использовать методы машинного обучения для того, чтобы работать вот с такими данными, но пока это ближайшая перспектива. Вот на данном снимке вы можете как раз-таки увидеть результаты детекции археологических памятников, то есть сопротивления магнитного поля в поверхностных слоях. Ну, вот это немножко глубже уже, на несколько метров, данные магнитометрии. Вот после того, как этот памятник был обнаружен, мы к нему также применяем известные методы, в том числе метод DGCNN, или как мы его называем, MGCNN, для сегментации его пространств. Нас прежде всего интересует здесь уже классы двух типов. Это, собственно говоря, наличие некоторых рвов и жилищные камеры. Ну вот как раз-таки результаты сегментации этого памятника вот представлены на данном слайде. Ну, здесь видно четко, что вот есть вот такое облако точек, и здесь градациями от желтого к красному обозначены рвы, ну а синим, зеленым жилищные впадины. Ну и вот таким образом получается без, в общем-то, раскопок определить расположение вот таких археологических памятников и понять внутреннюю структуру. Вот такой, в общем-то, щадящий дистанционный метод исследования археологических памятников, в общем-то, позволит археологам изучить без раскопа структуру, собственно говоря, археологического памятника, понять, где у него находятся, собственно говоря, рвы, где у него находятся жилищные камеры и так далее. Нами в работе были проведены, естественно, некоторые эксперименты в плане сравнительного анализа. Мы сравнивали как прямые методы, так и непрямые. Но для непрямых методов мы взяли мультивидовый CNN, ну, использовали, а в качестве прямого метода взяли DGCNN и использовали некоторые комбинации DGCNN с детектором YOLO. То есть использовали 2 канала информации. Ну, вот в результате таких экспериментов нам удалось выяснить, что вот для некоторых классов курганов К1, К2 и К4 получаются достаточно впечатляющие результаты, причем предложенный вот нами метод, вот он здесь находится в нижней части, он обладает преимуществами. Но вот такие классы, которые как К3 и К5, вот это так называемая дерновая распаханная поверхность или так называемые курганы с усами, они достаточно плохо детектируются. Как известными методами, так и нашим методом. Так что есть еще большое пространство для каких-то работ. Ну и на следующем слайде есть результаты детектирования уже укрепленных и неукрепленных поселений и могильников. Ну и мы видим, что вот как раз-таки применение нашего метода для сегментации и классификации поселений дает достаточно хорошие результаты, но по могильникам пока такими результатами похвастаться мы не можем. Ну, на этом у меня все. Спасибо за внимание. Вот еще раз извините за эту проблему, которая возникла. Ну и так-то я, в принципе, планировал приехать в Армению, уже билеты купил, но вот заболел. Ну, я дальше вот попал в такую нехорошую организацию, как инфекционное отделение госпиталя. Вот здесь сейчас я нахожусь. Вопросы?
Давайте поблагодарим докладчика. Мы немножко, конечно, выбиваемся из времени, отнимаем время на обед у коллег, но если есть вопросы у кого-то из присутствующих в зале? Да, у меня один быстрый вопрос, я знаю, что все хотят бежать. Мне очень интересно, спасибо за интересное исследование, мне интересны части данных, которые вы использовали со спутников. Насколько я себе представляю, большинство спутников, они делают съемку на различных длинах волны, и не только в видимом спектре, но еще и в других. Скажите, пожалуйста, это как-то используется ли в работах? Потому что, насколько я вас видел, у вас все в РГБ, то есть все из видимого спектра вычислялось.
Да, я скажу сейчас. Мы используем все каналы, в том числе как бы инфракрасные каналы. Мы не используем только какие спутниковые данные, то есть то, что снимается там, в ночное и вечернее время суток, и такие снимки бывают, но не часто это раз. И мы не берем, естественно, снимки, которые содержат облачность. Ну вот сколько мы не пытались, в общем-то, удалять эту облачность, ничего там хорошего не получалось. Поэтому вот берем, собственно говоря, все доступные каналы, но вот исключаем из них вот снимки, которые содержат некоторые атмосферные явления, облачность, ну и если попадают, такое иногда бывает, на какое-то вот неправильное время съемок.
Понял, спасибо. Спасибо докладчику. So, I would like to thank everyone. Yes, let's thank the presenter again. Yeah, I would like again to thank everyone for participating in our section, both online and offline presenters. Thank you for your contribution. Please have a nice rest of the conference.
Thanks to organize. Cheers.
Не страшно думать человек, понимаешь? Не наложит? Как бы, а на следующей конференции он уже никогда не пойдет. Конечно, такое.
Не, на самом деле ситуация сложная попала, но что удивило, что он нас не предупредил, потому что на самом деле он со мной несколько дней переписывался в Телеграме, спрашивал, вот я заболел, что мне делать и так далее. А потом вот самый ключевой момент, и он мне написал заранее. Не, похоже, что не он пять человек заказать. Не, он поехал быстро. Врач сказал. Фишка в том, что не то, что он заболел. Поэтому он заболел ковидом, его лечат в военном госпитале. Everyone in военном госпитале. В России запрещен. Я даже не написал.
Я почему скажу, если очень кратенько, то... Вопрос проект, если будет такой, вы как все отправить стороной? Ну, ничего. Тогда или как? Вот, такой номер приблизно. Понимаю, в чем вопрос. Для регистрации программы для РЛ нужно, чтобы был заказ. И вот если номер заказа будет такой, ну, как все отправить. Ну, почему нет? Я не вижу так противоречий.
Thank you. Hello, everyone, one more time. This session is on theoretical machine learning and optimization. And since, unfortunately, we do not have the session chair offline, let me start this session with my talk as scheduled. My name is Dmitry Ignatov. I'm from HSE University in Moscow, and I'm working at the data analysis and artificial intelligence department, and also chairing the lab, which is doing all sorts of machine learning and NLP, for example. But this talk will be mostly about theoretical stuff, I would say.
I'm sorry, Dr. Ignatov. Do you hear me?
Yes, I can
As
hear you.
I thought I'm a chairman of this session.
Yes, that's correct. But
so,
you are online. If you are able to introduce me in that manner, this is my pleasure to restart it. Okay?
Okay, dear colleagues, so we can start our session about theoretical machine learning and optimization methods. And we have only 3 presentations this session, so we can be more free with our time limits. But I ask all the authors, all the speakers to keep the regular time limit about 25 minutes, including the answers and questions. So our first speaker is my old friend and colleague, Dr. Dmitry Ignatov from High School of Economics, University Moscow. And I thought it is very, very interesting theoretical talk about mathematical logic, maybe formal concepts. So you can see his title. So Professor Ignatov, the hall is yours. You're welcome, please.
Dear Mikhail, thank you for the introduction. Let me start the talk. This talk will be about partition lattices and a specific problem, maximum anti-chains in partition lattices, their size and enumeration. I can't say that these results are, how to say, breakthrough results, but at least they would add some bricks to the current state of the art on the problem. Since our referees asked about applied introduction into the problem, I decided to include motivation from data mining perspective, and I omitted some theoretical stuff. Here is the outline of my talk. After that, I'm going to go on to the motivation from combinatorics perspective on the problems which are announced, and then we'll go through partition lattices as concept lattices. Then we'll consider the problem statement, actually 3 problems we are considering here. They are closely interrelated, and I will talk about our solutions of these problems, both the theoretical ones and the practical ones, meaning that we added some new numbers into online encyclopedia of integer sequences, counting the respective patterns. So motivation from data mining perspective might be well familiar to you. If you go to the supermarket, you can buy some stuff there, and some of the items you can buy frequently as many other customers on a daily basis. One of such product items, the collection of product items, was the diapers and beer. And here you can see 2 researchers from the area. One of them given a gift, diapers and beer, to the developer of the best algorithm in terms of, I don't know, performance time, which is able to find such patterns in the data. What kind of data we mean here? Those are transaction data, and they can be represented as binary tables, also in transaction database format, or maybe in vertical database format. But in essence, we have transaction IDs, 1, 2, 3, 4, 5, 6 customers, for example, or the same customer on different days, doesn't matter. And 5 items, A, B, C, D, E. 1 means that a particular person or a particular transaction contains a particular item. Here is just the same reformulation, but we have a transaction ID and also an operator I, which results in the set of items that were bought in particular transaction. And similarly for vertical databases, we have operator T, which says what are the transactions where a particular item was bought. It's closely related to inverse indices in information retrieval. But let's have a look at the result of this search performed by one of the algorithms, like a priori, for finding such frequent patterns. For example, we have item B, which was bought 6 times in a particular transaction database. So we also have item sets that were bought 5 times. So at least 5 customers bought together B and E. 4 times for this collection of item sets. ABE, for example, was bought 3 times. The minimal threshold here for the number of such purchases is called minimal support. And the structure which lies behind, the fundamental structure that lies behind, is the lattice, which is the lattice of closed item sets, or the concept lattice, as we call it in formal concept analysis. I will talk about it a bit later. So here we have some items with the same supports, like A. It was bought in 4 transactions, and also ABE. It was also bought in the same 4 transactions, and such classes form the partition. Those are equivalence classes. Actually, they have a unique representative, the closed item set. In terms of support, it cannot be extended without violation the maximality of support here in the respective class. And there are also the so-called minimal generators, but they are not necessarily unique. You may think of them as proper subsets of closed sets, which cannot be further diminished. Okay. What you can read in this textbook by Zaki and Meira on data mining, that the concept of closed item sets is based on the elegant lattice theoretical framework of formal concept analysis by Gunther and Wille, and we'll use this as a main tool for enumeration later. Also, I would like to mention some related works where not only such concept lattices are used, but also partition lattices, and we can show that partition lattices can be represented as concept lattices. Partition lattices may be considered as a search spaces for clusters if we solve the problem of partitioning or community detection in SNA. They also can be used for granular computing or for building functional dependencies in relational databases, and even for a variation of binary data analysis, which is called independence data analysis. Here are some of the links. But let's go to the theoretical motivation, which dates back to the problem of Rota, which was published in the Journal of Combinatorial Theory. He states the problem as follows. It's well known that for a Boolean lattice, the largest size of anti-chain, that is the family of sets which are not subsets of each other pairwise, is given by the middle binomial coefficient. And he proposed to prove or disprove the following generalization of this theorem. Whether for the partition lattice, the size of the largest anti-chain coincides with the Stirling number of the second kind. So it was his proposal. And since the name of Emanuel Sperner was mentioned, it's good time to mention that Emanuel Sperner studied Boolean lattices, and he formulated a theorem which proves that the central binomial coefficient gives the size of maximum anti-chain of elements or sets in the Boolean lattice. Here you can see two such anti-chains for the case of 3-element sets in red and in blue. And in its turn, the problem studied by Emanuel Sperner dates back to the problem posed by Richard Dedekind on the number of anti-chains in Boolean lattice. So the first one is the beginning of the 19th century, and the last one is the end of the beginning of 20th century, and the last one is the end of the 19th century. As for partition lattices, a lot has been done already by the end of 70s, and in the paper by Ronald Graham, for example, the co-author of Donald Knuth on a famous book, Concrete Mathematics, he summarized the state of the art by that time. You can see the partition lattice on 4 elements from his paper. Here you can see, for example, the level anti-chains. Here, for example, and here by R, the sets of elements of a certain rank are shown. So we will also use this terminology in slightly modified manner later. And what he told us in this paper is as follows, that at most for n less or equal to 20, the size of the largest anti-chain coincides with the Stirling number of the second kind. And unfortunately, we do not know whether discrepancy arises, but this discrepancy exists, and I'm sorry, don't know how to go back to the full screen mode with a touch screen here. Can you help me? And Rodney Canfield showed that the largest anti-chain actually is not the level anti-chain, so it does not coincide with the longest level in such a lattice. According to Canfield, discrepancy may arise for n, which is very big, and Ron Graham says that we will never know where it should happen. But at least Canfield and one of his and Graham co-authors Harper, they showed what is the size of such an anti-chain asymptotically from below, together with Harper, as far as I remember, and from above. That's the latest result by Canfield, but already in 1998. So the theorem says that the size of such maximum anti-chain divided by the Stirling number of the second kind, the maximal for the specific n, lies between these two values, where a is given as the constant is given as follows. And this paper contains the following statement: the symbols C1, C2, the constants here, for example, they denote positive real constants, and it would be possible to find them, but distracting to replace these by explicit values. So is Canfield right is the main question in the title of the paper. Just tell us that we need to have a look at these numbers, what they are. And we are going to use also representations of partition lattices as cross tables or formal contexts known in an applied branch of modern lattice theory. So here you can see cross table representing this partition lattice, but instead of this second level where the partitions of 3 elements should be given. We have only pairs of elements which are together in one block. It is done deliberately. Okay, what are the problems here to address? First, what is the size of the largest anti-chain for a given n? The problem was solved by Canfield asymptotically. And a few beginning numbers are known. We counted them explicitly. As for the number of anti-chains and maximal anti-chains, we also can count them explicitly, not asymptotically, but asymptotically it's also possible depending on this dp. The first proposition says us what are the constants. The constants are obtained from the first order conditions for this function. So it has its maximum and minimum on the left. It has maximum and 2, and x minimum is given by this n in integers. That's not integer if we compute it directly. And if a little bird would tell us where the discrepancy arises, we can refine the coefficients nicely. You may think that this is not a little bird, but just an oracle. Okay, we can find these coefficients, but in terms of inequalities, using the first order conditions. Moreover, since Canfield used this substitution for n in the original computations, we can use it as well, and we can use the principal branch of Lambert W function, which is given here as a graph, and refine these coefficients even for n greater than 1. So these coefficients, C1 with a wave and C2 with a tilde. Okay. So the proof is given here. So we simply took the final expression from the paper by Canfield and Harper and made the corresponding substitutions using our knowledge about the maximum value, that is first order condition. And similarly for the upper bound, and we used the form of the function and the Lambert function as well. Here, Bn, the rotated Bn, means Bell number. It gives us the size of the whole partition lattice, the number of all partitions for a given n. There are 2 remarks that we can recover this coefficient even for n greater or equal 1. That is, Canfield didn't consider n equals 1, but we can do that because of direct usage of Lambert W function. And similar propositions can be formulated for zero discrepancy intervals, that is up to n20, as Graham reported. The results of our computations, of direct computations with algorithms from formal concept analysis, both confirmed the results for the number of anti-chains in the partition lattice and for the number of maximal anti-chains in the partition lattice. This sequence was added by us and accepted by the OAS editors, Neil Sloan. So we somehow extended the state of the art and confirmed the known values. But what was the machinery? We used this binary representation. We used the resulting concept lattice. The numbers here are just binary codes, and you may think that they are IDs of the nodes in the lattice. And we order them according to this relation. and built another lattice, and this is the lattice of anti-chains. And if we simply remove the equality side from here, like here, oh, sorry, yeah, remove it, then the diagonal will appear. We obtain the lattice of maximal anti-chains in the partition lattice, and this is the case for N3. So for larger lattices, it's a fast-growing sequence. It takes a lot of time, and here you can see, for example, that from milliseconds for some of the beginning ends, for N6, we already spent more than a month, and our computation did not finish by that time. Now we have some progress, but it's not finished yet. Here there are some graphs, sorry for a small scale. We compare the number of maximal anti-chains in Boolean lattice and in the partition lattice. For N6, this red dot is somewhere here. What we are trying to reach, maybe it's better to have a look at these figures in the paper already. But we also try to formulate some inequalities bounding the number of anti-chains in the partition lattice from below and the number of maximal anti-chains from above. We used the level-wise partition of the partition lattice into anti-chains. So that's why we have this amount here mainly. But we also use interlevel anti-chains, meaning that if we have different levels, the elements, the sets of different ranks in the corresponding partition lattice, we can consider anti-chains from different levels and somehow improve those values. Actually, the improvements are good only for beginning values. So here delta means the discrepancy between the number of anti-chains and maximal anti-chains, and the L and the L plus are our inequalities. So for 1, 2, 3, this is zero relative error, but for 4, the maximum that we could get is 0.32, for 5, 0.57. So we need to count more elements. And as an illustration, I would like to mention the case for N4. Here you can see the binary representation of the corresponding partition lattice, or even 2 layers of the original partition lattice. And here we consider this relation on its partition, and we can count 30 patterns or 30 concepts or anti-chains, maximal anti-chains. And if we add 2 more, we exactly obtain the number of maximal anti-chains in the original lattice. Also using the tool, which is called lattice miner, we can build the concept lattice diagram, sometimes called Hasse diagram, but Hasse was not the first who used this name, so line diagram is a bit safe to say here. And this diagram can help us to extract all the other anti-chains, not only maximal, by hand. So we inspect those concepts. We consider different bipartite graphs, say with 3 and 1 vertices in different parts, extracted from the corresponding concepts of the corresponding levels. So here, for example, you can see that in one part there are 2 nodes, and in the other part there are also 2 nodes, but they are given as the corresponding partitions names. And we can sum all the total counters here. And also we should work not only with the concepts represented in this lattice, but also with proper bipartite subgraphs, not only maximal bipartite subgraphs. They are formal concepts. And count the types of anti-chains represented by bipartite graphs: 2-1, K2-1, K1-2,
Dmitry, I'm sorry,
K1-1. Yeah?
but your time was over 3 minutes ago.
Okay, the last slide here. When we sum it up, we obtain 344 patterns, and we also need to include this partition where all elements are in, and these partitions where each element in a separate block. And if you ask me about a single formula to compute it, you can find it here as well. Unfortunately, the time is over, and I'm only ready to answer questions. Thank you.
Thank you very much. First of all, I would like to ask the host to open my video, because it's not easy for me to have my own video on Zoom, please. And the second, I would like to ask all the colleagues to ask one or maybe two questions to Dr. Ignatov about his very, very interesting talk. So you're welcome, please.
Please open your video. It's not here. Yeah.
You need microphone. Okay.
No. He might not hear you because you didn't talk to the microphone.
I'm sorry. Your video is not on. We can't see you here.
I'm sorry, I cannot to switch on my video because host was prohibited this.
Oh, wait.
Or maybe we should go to the participants list and try to enable it somehow here.
Okay. This is weird. The reason is because this is not the host computer. Wait.
Okay.
I'll try.
Okay, thank you. So, Dr. Ignatov, would you like to ask any other question?
From my side, no questions, but we are expecting the questions from the audience.
Then I have a question.
Yeah.
Can I ask you my question? So, hello? Do you hear me?
Yes, we can hear you well.
Very nice. So, I like your theoretical work. It is very interesting for me. But our conference, you can agree with me that your topic is quite borderline according to this conference. So, please, could you explain in more detail the machine learning applications of your high-level theory in 2 words?
Yeah, so I would rather think about this topic and this direction as not theory for machine learning, but machine learning, and I would even say data mining and formal concept analysis for combinatorics. So we can take algorithms from data mining for enumeration of closed item sets, and we can compute these values, which are not yet known, at least in the OAs, and extend our knowledge. Maybe someday a new Euler will come and give us a nice formula, but so far machine learning helps us, and data mining, I would say, helps us to find this number, at least scrape them from the data.
Thank you very much. Such a nice cooperations between two fields of the theoretical informatics.
Yeah, and
yes,
it's really my pleasure to contribute to this section, which you chair many years, I believe, and thank you very much.
Thank you very much. Thank you. Very interesting presentation. Thank you.
So there are some questions from the audience. I don't know, Mikhail, whether you can see.
Okay.
I have a question. Your title includes a question, is Canfield right? So to summarize, is he right or not?
Yeah, it's a bit provocative question to attract attention to this kind of problem, because if you check, there were no progress since the beginning of millennium, because Canfield solved the problem theoretically, asymptotically. But these coefficients, should we know them? Should we try to know them? Is a very good answer, which can stimulate us. So Canfield decided at that time that they are distracting, but we tried to find them out. And maybe if we can prove theorems about the concrete n where discrepancy arises, we can refine these coefficients, and at least we know what is the gap. And this is nice. It might be like a competition. A new mathematician or practitioner will come and refine it more in a more elaborated way.
Okay.
Maxim Panov here would like to ask a question.
Yeah, I have also, I don't know, probably funny question, not really related to the topic. You had one of the slides where you were referring to some book or foundational paper where there were 3 authors, but you striked one out. Why?
It's also a funny story. The original book on formal concept analysis, mathematical foundation, is authored by Bernhard Ganter, one of my supervisors from the German side, and by his supervisor, Rudolf Wille, who passed away. Then they translated it into English. The translator was Franzke, and some of the systems indexed Franzke, but his contribution was not actually as an author, but as a translator. And in the community, we discussed it many times. We decided not to not to give his name, but at least I decided to give his name, but strike it out. Sorry.
Sorry, colleagues, we should proceed with our program. Thank you very much once again. And our second speaker will be Maxim Panov with his presentation about distributed by Gaussian core sets. You're welcome, Maxim, please.
Yeah, thank you very much. Thank you very much for the introduction. And yeah, that's my pleasure today to present this work that was essentially a master thesis, which was defended a year ago by my student, Vladimir Milusik. So, well, it would be more essential if he would be presenting this work, but he's currently a PhD student in University of Missouri, and it's, well, not feasible both to travel here and also to to speak online because the timing is not very good. So I will be presenting on his behalf partially, also on my behalf. Okay, so the topic here is basically the inspiration for this topic is Bayesian approach to machine learning. And well, we consider the standard parametric model like probabilistic parametric model where you have an input X, you have output Y, you have a certain probability distribution which is parameterized by some parameter vector theta. So it might be linear regression, might be neural network, it might be whatever. And usually we consider the situation when we are given with a data set, so pairs X and Y, so your historical observations. And then people write a likelihood function, which basically is joint density of Y's, joint probability of Y's. And usually it's convenient to rewrite it via log likelihood functions. And basically then the total likelihood is an exponent of sum of log likelihoods for individual data points. Well, I'm writing it here because for my future task it will be important, so such a representation. And in the Bayesian approach, you usually assume that there exists some prior distribution on the weight, defined as P naught on my slide. And then if you have a likelihood and you have a prior distribution, then you can write a posterior. So the posterior is given by this formula. So you have a product, so it's Bayes formula, well known, and you have this product of likelihood and prior, and then you have a normalizing constant in the denominator, which is basically just an integral over the theta. Well, if you think about some machine learning model behind that, what you are eventually interested in, you are interested in making predictions. So, and for this, people usually employ, in this Bayesian constant, people usually employ so-called posterior predictive distribution, where you average likelihood at a new point over your posterior. And in practice, usually, of course, you can't compute this integral explicitly, and people do sampling, like Monte Carlo approach. And I also should mention that, that because you have very rich object, potentially, the posterior distribution, then you are not like constrained by just looking on expectation. You can look on the moments of this distribution, on a variance, on other moments. So basically, you can also reason about uncertainty. And that's why generally Bayesian approach to machine learning is thought to be like an interesting thing, because you not just do a point prediction, but also you can do certain uncertainty quantification. However, these formulas are a bit problematic because of different things. So the mainstream, I would say, problem which people consider is that actually the numerator, denominator is very problematic to compute. So numerator is given, you have some prior, you have a likelihood, it's all given. But in denominator, you have something which is an integral, and this integral is hard to compute, usually. So of course, there exist cases like case of conjugate distributions when it's easy to compute, but in general case, it's hard to compute, and people consider various approaches to sample from this distribution or to approximate this distribution. So most well-known are Markov chain, Monte Carlo, and variational inference. However, in fact, if you consider like modern applications, when you have a lot of data, like think of modern like image classifiers, which are trained on millions of data, or think of probable language models, which are trained on trillions of data, there is another part which is actually might become complicated to compute. That's likelihood itself. Why? Because the summation is very large. So you have many, many summands, and then imagine you want to do Markov chain Monte Carlo on top. What is Markov chain Monte Carlo? You iteratively try different points until you get something which is accepted and which is your generated sample. And well, this process requires to evaluate likelihood very many times. And if it's n is million or billion or trillion, it might be very, very hard to compute. And that's why in the research community, it was considered like certain approach which is called core sets. basically what you do, you consider the weighted likelihood. So you introduced weights Wi, and you want to construct these weights in such a way that first you have many zeros among the weights, so you reduce the summation. And second, that this posterior is close to the initial posterior. Okay? So you want to select some subset of points which approximate, possibly weighted. So it might be not 0, 1, it might be something else. But you want to have many zeros, and you want to have a small subset of points which well approximates your initial distribution. And then, if you succeed with this task, then you will be able to do your computations very, very quickly. I mean, if number of non-zero W's is small. Well, basically a little bit the same notation again. I'm sorry, I just want to mention that we almost, in the experiments later, we almost wouldn't consider the problem of supervised learning, which motivated the problem. And we mostly will consider the problem of density estimation and sampling from this density. So that's why I'm writing just as I have just X here. But essentially, it doesn't change the formula for posterior. And well, there exists quite established literature on the construction of core sets, including Bayesian core sets. And actually, all the algorithms we are aware of, they follow more or less the same structure. So what you do, you introduce some distance between the log likelihood functions. And one possible distance might be expectation of the posterior over the posterior of a difference of log likelihood function. Yeah, and then what you do, you want to find the weights which minimize this distance between the full posterior and your weighted one under the constraint that you want to have not more than k non-zero weights. So that's a certain optimization problem. It, of course, depending on likelihoods here, it can have kind of a different complexity. However, well, that's a general approach. One useful notion which was introduced in the literature and which helps a lot is so-called notion of sensitivity. Basically, you look on the ratio between the likelihood of one point and all other points. And if this ratio is high, then probably this point is important and you should include it. If this ratio is low, then point is not important and you exclude it. And to have, but of course you have a free parameter theta here, so you need to do something with it. You can say, okay, my definition will be via supremum, like the worst case or the best case, depending on the look, what is your contribution to this likelihood. And this notion is called sensitivity. And the majority of works, they consider different algorithms based on these sensitivities. Of course, well, it's a big question how you compute them. I won't touch it in this talk. Well, you need to do some approximations. And basically, the works which currently exist, they basically have two main parts. First one, you either can do iterative methods, which gathers the core set step by step. So you choose one point, you choose another point, you choose third point, and so on. Or you do sampling. So if you do sampling, it's actually pretty easy. You sample random points with probabilities that are proportional to sensitivities. So, and then you get something. In sequential approaches, you try to choose the point which improves your current score the most, and you do it one by one. And the main difference between the methods who are iterative is whether you try to like solve, if you consider this functional exactly, or you may try to convexify this constraint somehow. Okay. And the question which we asked in this research is, well, the iterative approaches, they in fact give pretty good performance in practice usually, but they might be very slow because you choose points one by one, you have a huge data, your final core set will be much smaller than the whole the data, but still pretty large, so the process can be slow. Can we parallelize it? And in the literature, there were considered like some works which were doing this parallelization for non-Bayesian sets, which consider just approximation of likelihood without any posterior. And we wanted to do something for this Bayesian approach. So, and basically, well, very simple idea. Actually, the idea of this work is pretty simple. That what we want to do, we will be sampling, so we have a data and we will be sampling a points from it based on the likelihood values. So we have some, say, maximum likelihood or maximum posteriori estimate of the parameters. We plug it in and we sample points proportional, without replacement, proportionally to the ratio, which we obtain for this fit ahead maximum likelihood. And basically, we expect then that on different, and what you actually do, you sample several points for the first computer, so we do distributed computations, then several points for second and so on. And hopefully they will be sampled in a way that sort of form clusters. So first you probably will sample the most probable points, for the second, the less probable points will go and so on. Yeah, so that's some, yeah, so once again, we have several workers or processors or computers. We will do course set selection on each of them separately. So first we sample points, then we do course set selection for them separately, and then we merge the resulting course set. And each of them has a size of a course set k over the number of workers. So, well, what are the results? So we, in this work, we considered, well, pretty simple examples. So we start from just density estimation and Gaussian data, which is very simplistic. First, let me explain you which algorithms are compared. So we have 3 algorithms. So one is a baseline iterative approach called, I don't know why called sequential here, but well, it's a synonym. And then we have 2 distributed approaches. One is based on a random splitting, and the other one is based on our, well, we call it machine learning split, our sampling proportional to something, to sensitivities. And we present 2 plots. First of all, on the x-axis, we increase the size of a course set, and on y-axis, we compute the KL divergence, so the distance, the smaller the better. And on the second plot, we represent time computed in seconds here. So basically what we see that for the multivariate Gaussian example, so, well, very simple problem, of course. And we observe that here sequential approach works better. So our distributed approaches, when we distribute and then merge, they work worse. However, well, as expected, they work much faster. So here I think we had 7 or 8 cores working in parallel. Then more interesting things start to happen. So if we look on the Gaussian mixture, first univariate Gaussian mixture, then already the distributed methods, they start to beat the sequential approach. Why? Because sequential approach is greedy. And what I expect that, well, probably we need to do a little bit more in-depth analysis, but what I think that basically different cores, they successfully approximate pretty accurately different modes of our mixture. So each of them becomes good at one mode, while this one is jumping from mode to mode and something weird happens. So, and here already we see certain improvement over the random split by ML approach. And well, computationally, we see there is a big difference in speed compared to the sequential one. Then we considered multivariate Gaussian mixture. Here it's more or less the same story. Pretty good gap between sequential and ML and distributed approaches, and a certain benefit of using better sampling. And probably the final plot which I wanted to show, that's a bit different. That's already supervised learning. So there was some classification problem. And what we do, we report the resulting accuracy of classification. So what you do, you make a course set, And then you use some Bayesian model for classification based on this curve set, right? So instead of full likelihood, you use a weighted likelihood. And what we report here now, it's not a KL divergence, but our downstream quality, so the accuracy, right? Well, what is nice that at least accuracy is improving with curve set size, so we sort of get more information. And also what we see that interestingly, the distributed approaches are doing kind of better than the sequential one. So again, we actually benefit from distribution, not only in terms of time, but also in terms of quality. And probably the final plot I wanted to show is the dependence on the number of the processors used. So generally what we see is that you can get an improvement when you increase the number of processors. There's some fluctuation here, not sure why, but generally we see the trend for improvement. And also, well, you see the improvement in time. The more processors you have, you improve your computations, or apparently diminishing returns. So it's not linear. Well, everyone would be happy if it's linear decrease in time, but it's in fact it's not. So there is certain overhead. Well, that's the same. So, and well, to summarize, so I think really, as you've seen, we really scratched the surface. However, generally my motivation to start this work was actually to use these Bayesian core sets for actual computations, for example, with neural networks. Because currently Bayesian neural networks, well, you can find many papers in top conferences, but eventually you see that there are little to no benefit from their usage, because it's either, because usually you can't apply them to really meaningful data sets. So you take almost any Bayesian neural network paper and you end up classifying MNIST, not anything like ImageNet or something like that. Why? Well, you need to do MCMC over rational inference on hundreds of thousands of parameters on millions of examples. That just doesn't work. So, and I think that here we need a kind of a combined approach. So we need to use core sets, we need to use parallelization, and we need to some advanced variational inference or MCMC algorithms. So that's some very small step in this direction. So I think I'm done, and thank you for your attention.
Большое спасибо. Коллеги, пожалуйста, задавайте... sorry. Thank you very much. Dear colleagues, please ask your questions to the speaker.
Thank you for interesting talk. In the beginning, you were talking about the distribution of parameters, prior distribution. So how you choose this distribution?
Yeah, thank you very much. That's actually the question I think everyone not from Bayesian community is asking all the time. And there is no like a final answer on that. So there exist different approaches. One of the approaches that you try to use the distribution which is like disturbing your likelihood as small as possible. So I forgot the name in English, but basically something which has actually very flat. So something which doesn't put you somewhere. And I think it's kind of a reasonable approach for large-scale applications when you actually don't have any idea. However, I also should mention that for modern modern models like neural networks, generally the question what should be good prior is very, very open. Why? Because, well, putting a prior on each weight from 100,000 being some Gaussian, well, does it make much sense? It's not very clear. And the final point here is that on some like smaller scale applications, sometimes people have kind of a domain knowledge. So if you have a, I don't know, linear or logistic regression, then the practitioners might have some idea what kind of weight should be for the particular factor. Then you can have some Gaussian around this value on some, or I don't know, uniform distribution on some segment, and you can use that.
Thank you.
Any more questions?
Okay.
Maybe one question on terminology. I like the term core set, but maybe you know about its origination. Why these two words?
That's a very good question. Actually, I don't remember the paper where it was introduced, so I will need to look. So actually, this area is relatively rich, and there are more general definition of core sets. For example, here I used only weights, but sometimes people want to have a kind of a synthetic examples. So you start to tune your X so that you can approximate the whole likelihood with a few points. So generally, it's a kind of a broad topic. Well, I will do my research and send you where it originated from.
Excuse me, colleagues. Can I talk some words about answer of the Dr. Ignatov?
Go ahead, please.
It seems to me that this concept, core set, initially was introduced in computational geometry in the context of Bronimal-Goodrich approximation algorithms for the so-called heating set problem. So it is very, very interesting combinatorial optimization and computational geometry problem. So it's very interesting for me as a specialist in combinatorial optimization to listen to your presentation, because it is also one more proof of the deep cooperation between machine learning and combinatorial optimization. Thank you very much. Very interesting.
Thank you, Mikhail. It seems there are no more questions in the audience.
Okay. Thank you again. And now we, sorry?
I think we have an online talk, right?
Yes, yes. We can proceed with our final talk. The least, but not, the last but not the least, by Professor Eduard Khaldinich Gemadi and Alexander Stepa on the problem of finding several given diameter spanning trees of maximum total weight in a complete graph. So it seems to me Alexander will be the speaker. Alexander,
yes, can you hear me?
Yes.
Oh, okay, I just.
So you're welcome, please.
Share screen.
Please share your screen, please. Okay.
Do you see it?
Yes, yes.
Okay. Hello, my name is Alexander Stepa, and I want to present our work with Eduard Khaldinich Gemadi about the problem of finding several given diameter spanning trees of maximum total weight in a complete graph. First of all, let's formulate this problem. We have arbitrary edge-weighted complete undirected graph G and positive integers m and d, which satisfies the following inequality. And we want to find m-joint spanning trees T1, Tm of the maximum total weight of edges in these trees and diameter equals d. Let us remind that the diameter of a tree is the maximum number of edges within the tree connecting a pair of vertices. This work is based on two works by us, which was published in 2022 and 2023. In the work 2022, we consider one maximum weight spanning tree with given diameter, and in the work of 2023, we consider several edges joint spanning trees, but for minimization problem. And we want to reduce our problem with several maximum spanning trees to the minimum case. And it done by using statement from this work. We have two graphs, G and G prime. In graph G, there is a weight function WE, and in graph G prime, W prime E. And there is a tree within with total weight, which is calculated with W prime. Then and only then, if it's a tree with such weight constructed in original graph G, and weights of function weights are linked by this relation. So we apply algorithm from the work of 2023, where we solve the minimization problem. So we have input-output of this algorithm and some steps. Let us describe them by the example. And we prove in this work was proved the feasibility of the algorithm and the time complexity of this algorithm. So we have initial complete graph. I want to describe the steps of this algorithm. And we have two spanning trees which I want to construct, and the diameter of each tree is equal to 5. So we choose two subsets, V1, V2, with D plus 1 vertices, and all other vertices we put in V prime. On the first step, we construct Hamiltonian path using a heuristic go to the nearest unvisited vertex. Of course, it's not exact solution, it's just approximate solution. And then we divide each path into halves and connect first half of the first path with first half of the second path by the shortest stage with inner vertices. Then second half of first path by the shortest stage within the vertices of second half of the second path. So we do it in a parallel manner, and then we connect this path using cross manner. So we connect first half of second path with second path, second half of first path, and second half of second path with first half of first path. It's done to avoid the possible dependency of random variable during work of algorithm. If we just connecting in another way, we can consider one edge twice, and it will break the independence property of random variables. And on the third pass, third step, we add edges from V prime and connect them again with the shortest path to inner vertex of corresponding trees. Of course, it's obvious that we connect with inner vertex because we do not want to increase the diameter of constructed tree. So if you connect with inner vertex, the maximum distance between trees will be on the path. But it was a description of algorithm for minimization problem. We want to solve the maximization problem, and this done by changing the weight function of graph G to weight function V prime, obtaining graph G prime, and apply algorithm A prime to the graph G prime. So we on step 2 we solve the minimization problem, and the constructed spanning trees T1, Tm are solution for the maximization problem. And again, in this work, we prove feasibility of this algorithm and time complexity, since a change of weight function can be done in O from n squared, and as was mentioned previously, the second step is performed in O from n squared time. So the total time complexity of algorithm I is O from n squared 2. There are some notations that must be introduced by F sub A from I and opt from I. We denote respectively the approximate obtained by some approximation algorithm and optimal value of objective function of the problem on input I. And we said that algorithm A have performance guarantees epsilon delta if such inequality holds, where epsilon is estimation of relative error and delta is the failure of probability, which is equal to the proportion of cases when the algorithm does not hold the relative error epsilon or does not produce any answer at all. And we say that approximation algorithm is asymptotically optimal on the class of input data if epsilon and delta tends to infinity as tends to zero as n tends to infinity. It's quite common common definition for probabilistic analysis, and we want to prove that algorithm I is asymptotically optimal. So it means that epsilon and delta goes to zero as n goes to infinity. There are some qualities which are used in the probabilistic analysis. If we denote random variable equal to minimum over k variables from the uni 0, 1 by xk and w prime from a prime be the total weight of trees t1, tm constructed by algorithm a prime. So it's obvious that this w prime a prime will be equal to sum of weights which are added on the first, second, and the third steps of algorithm A prime. So on the first step, we just use heuristic go to the nearest unvisited vertex. So on the first step, we have d possibilities because set contain d plus 1 vertices, then d minus 1, and etc. to k equal to 1, where we find the minimum over 1h, and this repeated n times. On the second step, we consider all the pairs between of the pairs of paths and construct edges connecting them. So we have a multiplicator C from C M2 and then connect four possibilities for edges and for end vertices. The first summand is for paths, and the second one is for end vertices. And on the third step, we repeat m times the connection of each from n minus m multiplied by d plus 1 vertices from set v prime, and connect them by the shortest edge to inner vertice, and there are d minus 1 inner vertices in each path. And according to statement which was mentioned on the second slide, we have obtained such equality, which connect the weight of graph, the weight of result of graph A and the weight of result of algorithm A prime. And we prove the lemma, which postulates the epsilon and delta for our algorithm A for problem for maximization problem. And the crucial statement for our analysis is theorem by Petrov, which consider independent random variables x1, xn, and introduce constants t, h1, hn, which satisfy the following inequality. And if we set s equals to sum of xk and h sum of hk small, we can obtain such probabilistic inequality, which will be which helps to carry out our probabilistic analysis. And there are some statements, some lemmas from our work 2023. In the first lemma, we prove that condition of Petrov theorem holds. And in the second lemma, we bound h big from above. And in the third lemma, we construct the upper bound for mathematical expectation of weights which get by algorithm A prime. So we reduce the problem of maximization to the problem of minimization and use some results for the minimization problem. And the main result of our work is that if D is equal or greater than logarithm n, then we get the following failure probability and the relative error. As you can see, failure probability is immediately tends to 0 if n goes to infinity. But for epsilon, it must be considered the case when D is D goes to infinity as n goes to infinity, as in the case of D greater or equal than logarithm n. And it must be noted that similar results are obtained for uni in a sub n, b sub n, since we can always reduce the problem with arbitrary a n and bn, which holds these inequalities, by reduce this problem to normalized random variables which are distributed on the interval from 0 to 1. And in contrast to the case of minimization problem, there is no need to impose additional condition on the scatter of h weights like was in the work of 2023. And as a conclusion, we can say that we have generalized result from work of 2022 for one maximum spanning trees with given diameter to several adjoint spanning trees, and use algorithm from this work, which has a time complexity O from n square, and applied it to our case with modified weight function. And for continuous uniform distribution of h weights on interval 0, 1, we can get an analogous result follows from continuous uniform distribution of h weights on interval a sub n, b sub n, as I said previously. And it will be interesting to investigate this problem on discrete distributions. Thank you for your attention.
Thank you very much. Colleagues, would you like to ask some questions to Alexander?
It seems there are no questions.
In this case, I would like to ask some small question.
Yes, yes.
So, Alexander, your brilliant work seems to me as another nice example of cooperation between machine learning and combinatorial optimization, and this field developed by Professor Gimadi and you seems to me very, very, very interesting in the case of our millennium problem about P and NP. So that's very, very interesting. And question is as follows. In your proof, you use Petrov's theorem, which appears to be a classic measure concentration result and classical result. Since that result, there are many more novel results, more strong measure concentration results. Would you like to incorporate them in your framework?
It will be very interesting. I'm not professional in this domain, but I think we just we should watch other approaches.
So thank you very much.
Thank you.
Thank you. So other questions, please. Oh,
Unfortunately, no questions.
it seems to me that all are clear. So we should thank our presenter once again. Thank you very much.
Thank you. Thank you for
And dear colleagues, unfortunately, I should close our session. Thank you for you all for a very interesting presentation and for the attention. Thank you very much.
Thank you, Mikhail.
Thank you.
Okay, dear colleagues, I'm just reminding that the parallel session is still going on, so we can go there. And also in 1 hour, there will be a poster session. So you'll have some interesting posters. So please attend.
Thank you very much. Okay.
А он уже готов. Все отлично. Сказали, что в какой момент для Ивана расширили электричество. И они искали распечатать. Если у тебя уже распечатали. Все отлично. Хорошо.
Die Maßeinstellung ist da anstatt so, policiert anstatt